Hello. Hello, everyone. Hello, guys. Wait, I'm sorry for the delay. Something happened like the last minute. Um, hello. Okay, so yeah, I'm 1 minute late. I'm sorry. I'm sorry, everybody. Uh, let's see. Unpin this message. Okay, I unpin the message now. Uh, is this the guy who I wanted him to? All right, buddy. Yeah. I think something. Teach us something. Yeah, it was 25. Wait, what do you mean by 25? Huh? Hello. 1 minute ain't that bad. Let's go. Yeah, agree. All right. So, we're gonna now. Oh, 25 seconds. Okay. Yeah. So now we're gonna we're gonna continue with what we've been doing today. Um, give everybody some time to come back because we were having a break. We had been streaming for like 6 hours, 5 hours, and this is the second half of that. So yeah, hopefully. Yeah. So currently, hello everyone. So we've been looking today at the tests and everything, and we sort of took a break in between just to start creating some sort of fuzzer, right? Some sort of like random tests for our memory allocator that just do like a bunch of stuff, right? And so with these tests, we can have a little bit more confidence on what's going on, I would imagine. Um, yeah, so it's good to have them, and that's exactly what we're gonna keep on doing. And yeah, so the question is like, how are we going to do this, right? Because we sort of need to perform like multiple operations. We need to malloc, then we need to realloc, then we need to freeze something, and then we need to, maybe malloc, realloc, and so on, and create a sort of sequence of random operations that allow us to stress test the memory allocator. What does that look like? Not completely sure, because well, what does that look like? We know what it looks like because I just described it, but we need to find a way to actually execute it. Right? How do we decide among a set of actions, which action to execute? You may say, oh, just have it generate a random number between 0 and 2, and then just pick whatever action that is. We are a little constrained, though. We're constrained by free. Because once we free something, we cannot free it again unless we have unless we have allocated something there. Uh, so I guess maybe we just never, maybe we just never what? We just never allocate like stuff. I don't know how to say it, but yeah, maybe we just never, after something is free, we just don't use it anymore. Like at all. And so yeah, I guess that is the way to do it. Um so what we can have is we could have some sort of vector, right? Some sort of vector or stack or some sort of structure that keeps track of all of the things that have been created and freed and etc. And then with it, we can simply, you know, just start putting this. Now with this allocator, we can finally allocate a 2 GB girlfriend. All right, fam, yeah, bro. But yeah. Oh wait. I'm gonna attempt to make a redstone computer in Minecraft. Here at 10. I remember DeFerrari was looking at like some Minecraft computers in his stream last time. That's fun. But yeah, okay. So so how are we gonna do this? We're going to, let's see, pick some action, and then we need to determine whether we want to perform this action on, an already existing block or something like that, or we want to do something else. I feel it would be so easy in C++ because then you have containers and then you can just do vector dot push back and then push it back and so on. Um, hmm. So what can we do? We pick a random action, right? Then we need to pick, if it is free, we need to pick who is gonna get freed, and that is an issue because like we don't have um, as many things as we think we do. Um, yeah. So there's that, right? Sorry. Okay. We pick some random action. If it is malloc or realloc, well, if it's malloc, then no problem because then that just creates a new block. If it is realloc or free, we need to determine who is going to be the victim of this action. And so we need to keep a list or some sort of system that keeps track of the things that are free and the things that are allocated. And that allows you to pick from each list something that's free, something that's allocated. Yeah. And then after that, what do we do? Well, not much, I suppose. Um, yeah, right? Yeah. Then after that, just, you know, continue our path. Wait. Okay, I'm struggling to think how will we keep track of the free blocks, the blocks that are allocated, if we don't have containers in C. I guess Evan, hello, Penguin operator. So currently we're trying to plan our fuzzer. We're trying to see like how we're going to do the random testing. The idea is we pick some action. If that action is malloc, then it's fine because it just creates a new block. If that action is free or realloc, then we need to give it as argument a block that already exists. So now we need to pick a block. And the thing is, we cannot give it like any block. It needs to be a block that is currently allocated. And so how do we pick such a block, right? Because like we don't have containers. We could implement a container from scratch, but I feel that's a lot of work. Um, can we just not? Can we just do it like in a, normal way or something like that? I unfortunately don't think so. Can we? How do we pick an allocated container? All I can think of is container, like an allocated container, an allocated block. All I can think of is containers, especially like a stable index vector. Um, yeah. Is there any other way? I guess we can also just like have a bitmap of which blocks are free, which ones are not, and then we just run it. If whatever we pick is free, then we run it again and we run it again until we find something that's actually allocated. Um, it would be kind of funny though. So like, it just increases the memory usage by like incredible amounts. Um, yeah. Okay, I don't know what to do. I don't know what to do. I don't know what to do. Hmm. Hmm. right? Because so what I'm proposing is something like, then for like int I equals 0 and then I is smaller than like 10,000, perform 10,000 operations. Then we do pick random operation. If operation is malloc, then just, we sort of would have something like this. Num blocks. The num blocks is 0 because there are no blocks. If the operation is malloc, we simply increase the number of blocks. And then inside some sort of blocks array, which we keep track of. So blocks, which would be a block array of, say, I don't know, 10,000 blocks. 10,000 blocks. I would just do like blocks at I, or like at num blocks is equal to whatever this new block is, right? So create block of size, and then here I append a random size, right? So something like this is what I'm thinking of. Then the problem is if the operation is not malloc, then we need to do something very specific, which is pick a random allocated block, which we're going to refer to as allocate block, right? And then what we do is we either, from the action we picked, action, we're going to have to call alloc block, comma, random size, right? So things are going to look this way. To know whether or not the chosen operation is malloc, we need to, okay, let me search something. How to generate a random number in C. C random numbers. Oh, 17 years ago. What the hell? That's impressive. 17 years ago. Wow, okay. Don't just rant for security. If you need to cryptographically. Oh, this is fine. Okay. So you include time. I'm just gonna copy this, right? Send that library, then do srand with the time null, and then just run rand. A pseudo random integer between 0 and 1. Between 0 and rand max. Okay, perfect. So then what we're gonna do is we're gonna create a function here that's called run number or randint, just like Python. Wait, you go offline and online, XT, so just breaks? Oh, yeah. So we took a break. We took a break of 1 hour, and now we're continuing. Let's go. So yeah, and then you're gonna have to pass me the bound. What is the maximum that you want? And all I'm going to do is I'm going to execute into my setup, right? Void setup. Into my setup, I'm gonna do something like srand, and then time, and null. And I assume that I need the time header. Yes, perfect. And SEMA S1. Oh wait, those keys make good noises. SEMA S1, welcome to the chat. Yo, you've opened Stack Overflow and I've realized that I haven't done that in a while with Claw. Yeah, it hits hard. Yeah. Yeah. So what we're going to do here is we're gonna run the setup after every end-to-end test. And actually, never mind, we're gonna run it over here. Why are my functions like this? Okay, there you go. Perfect. And so now when we pick a random operation, we're just going to pick a random integer. Operation is just going to be equal to a randint, and then, 2 is the maximum. And it should be inclusive. So what we're going to return is going to be rand modulo whatever the max is plus 1. Yeah, I think this is good. Of course, operator, precedence goes like this. And that should give us a number between 0 and whatever the maximum is inclusive. So then we have this, and then we say, well, if the operation is malloc, so let's make malloc the first operation at 0. And then we create a size random. So randint, then we make it be like, I don't know, what could the maximum be for a block? 256 bytes. Actually, no. Well, we would run out of memory very fast. So 256, yeah. And then we're gonna pick a random allocated block. Sure. So now the problem is, how do we pick a random block of the ones we've already generated? Oh. Right? Like, how am I supposed to do this? How are we supposed to do this? How are we supposed to do this? So I don't want it to, like, we don't have a need for it to be efficient. We just want it to catch bugs. So maybe I can genuinely just do, like in the struct here, I can just pick something like, bool free, whether or not the block is free. And whenever it gets freed, I just say block.free is equal to false. Whenever it is created, block.free is equal to true. And then whenever it is created, I just do block.free is equal to true. Sorry, the other way. Block.free is equal to false. Perfect. And then after that, once you create the block and do everything, we can just do like, block bk. Well, I would say block pointer, right? Block bk, or a reference to it. Block reference. Block bk is equal to what? To blocks, and then get some block that is the product of a random integer between the number of blocks. Right. So we pick this guy. Oh, C doesn't have references. Okay, great, thank you. Logs, and then I pick this guy apart. And then we say, okay, while block block is free, then we just keep choosing a different block, right? Like, this is very naive, I agree, but like, it is what it is. Like, yeah. So we just do block.free. Actually, no, I do want the pointer this time. Never mind. So here, and then we say block is going to be equal to blocks at randint of the number of blocks. And then we do that until we get something that's not free, right? Branch condition evaluates to garbage value. What do you mean, brother? Huh? Wait, free is a bool. Do you guys see the problem? What is the problem? Hello? Okay. And then what I do is then I say, well, if the operation was free, so then I say this one's free, and this one is malloc. So malloc. Perfect. If the operation is free, then we're gonna say, well, block free or free block. Free block with this specific block, and that's it, right? And of course, we just dereference it. And then here we call realloc and say, well, if the operation is equal to 2, then we need to reallocate. So then I say, you know, the value of this guy is going to be equal to realloc block or something like that. Which block will be k, of course, dereferenced, of course. And the size is just going to be a random integer until 256. And that should do it. I don't understand why it says branch condition evaluates to a garbage value. Brother, what do you mean? What do you mean this is a bool? This is a bool. Branch condition evaluates to a garbage value. Assuming taking the false branch on 222. Yeah. Branch condition evaluates to a garbage value. Brother, what do you mean? What do you mean? Huh? Anyways, that's okay. I'll just run it like this. And then after that, we return true because everything succeeded and we're happy. Pick a random operation. If it's nalloc, then allocate. If it's free, then free. And if it's realloc, then realloc. and that's it. We just perform 10,000 times an operation and hope for the best. Yeah. I feel 10,000 times is a little exaggerated. Let's do 10 of them, right? The problem, of course, is gonna be like, what happens if we just don't find a free block? See, this is the reason why. Okay. So I guess that if op equals 0, and then I'm gonna say uint32t, uint32t free blocks is equal to 0, 2. And whenever we increase this, sure, it goes down. But then whenever we free the blocks, we say free blocks. Well, actually, no. What the hell am I talking about? Yeah, free blocks, and then plus, and then whatever. Right? Right? I think. Wait, so what's... which plugin or tool gave you the diagnostic in orange in front of code? Example, line 229. Like, I don't know. I think it is the C extension itself. So, do you mean like what generates the little orange guy? Or do you mean like, let's try and solve what the hell branch condition evaluates to garbage value means in this case? I don't understand why it would say this, right? Because block is a struct. It has a member called free, which is a bool. Did I have to just say true? The left operand of this is a garbage value. Brother, this is not a garbage value. This is not... Okay. Oh, the branch. Okay, the branch message. So the thing that gives you this, the extension that gives you this, is an extension that, if I remember, it's called error lens. Yeah, error lens lets you like highlight stuff like this. So it's like, it's very pretty because then you're like, you see it and you're like, ooh, let's go. But yeah. And it's currently telling me that this thing is a garbage value. Oh, no, it was the C extension. Like you can see it here, C/C++. And then it's like the C-line analyzer, right? So now it's the Z-line type, yeah. is it's telling me it's a garbage value, but I don't understand why, right? Because this block is fine. The random integer generated is within bounds of num blocks, which we know to be populated. And then random int, all right? Why do I keep valuable time? I I don't know what to do now, because I wanted to create the fuzzer, but it. Okay, no, yeah, I'm tired of. I'm tired of this. Let's just go with the thing we had before. Let's just do deterministic tests for now. I think it's just gonna be better. Like, genuinely tired of this. Yeah, let's just delete this. I don't like this because then we need containers and stuff, and the C++ would be great for that. But I don't know. I don't know. I just don't want to. Let's see. We're going to play with say 10 blocks, right? And so what we're going to do is we're going to go through all of them is equal to 0. I is smaller than 10. And then we're going to just give them random sizes, right? So blocks at I will be equal to create a block. Create a block, and then I'm just going to call randint on some value, like 256. So 256 is the maximum size. And I feel like it's better if I include a minimum on randint. Where is randint? Here you go. We go to min. Min is this, and so now we add min to whatever this is. Right? Perfect. And so now we can include a minimum over here. So I want it to be between 1 and 256. So those are the blocks. That's the block size. I'm going to return true over here. So what are we going to do now? Well, we're going to say, now that we have these blocks, I want to, I don't know. So let's see what happens with, say, free block number what? Free block, and then blocks at, maybe with free number 5 plus 1 minus min. Ooh. Are we wait, are you sure? Because that could potentially give us a 0, which is not within the range, right? But it's also true that mine is also not within the range. So I guess yeah. What you're saying would be something like this, and then we add min to it. Yeah, that makes sense. Perfect. So over here, thank you very much, Bambi Capello. Over here we can maybe free block 5, right? And maybe we try to, I don't know. See, I'm a little trapped. Like, I'll explain what I'm saying. Like, I wanted to create random tests, right? But like the absence of containers in C is killing me. Like, I don't like it. I don't like it. I want to go back to C++. And the reason is because, like, we need to keep track of which blocks are free and which blocks are allocated so that we don't do a double free if we're generating random tests. And so, like, you know, how do we keep track of the free blocks? It's like, So I guess I would just have to implement my own container just to do tests, which I guess is relatively easy, but like it's kind of annoying to be completely honest. Yeah, because what we had before was precisely that. Here, this is what we had before, where you would pick a random operation and then perform that operation with like a bunch of random values. And yeah, and so yeah. The thing is, I need a container to keep track, to efficiently keep track of which blocks are free and which ones aren't, so that I can have like a vector of stuff and then just eliminate the things that I don't need anymore. I guess I do more if I just implement it, right? So stable into svec stable let's call it svec, right? A stable index vector, and we're gonna code that in C. And then we're going to create a file called stevec.h. So we're going to have multiple functions. The first one is going to be to insert stuff. So stevec insert. I hate this so much. We're gonna let's just store numbers from now. So value. We're gonna have to insert stuff in there. We need to also create some sort of struct here that does that, and then I can call a stevec is exactly this struct. And what this struct contains is a array of numbers, which it's going to call the IDs, and say it has, I don't know, just some random value, 100, no idea, in 32t, and then we're going to have elements, and that's going to also be 100, and then nothing else. I think we only need those two. To include that, I think we need to do, of course, a pragma once, and then we need to include the student.h, I think. That's where the UN32s are defined. Yeah. So we're going to just create our own stable index vector real quick. We're going to need to have a counter here. So static. Oh wait, actually this is not implementation. So yeah, stevec insert. Perfect. Void stevec remove, and then you need to give me the ID of the thing that you just removed, ID. So I guess that when I insert, I need to give you the ID. The ID is EN32T. Insert and remove, and that's kind of it, right? And then void stevec at, and then for that you just need to give me the ID. More like stevec get. And yeah. So, oh wait, it's calling me, but I'm currently creating this. In a second, stevec c. Now I'm gonna include the stevec.h library, and then what we're going to do is we're going to implement each of these. So for insert, I guess we first need to have a something that returns a stevec and it's called stevec. Well, create a stevec, and what we're going to pass to it is the size of the stevec that we want. Maybe question mark. Not really. I'd say yes, actually. So IDs and elements, they need to be a little less. Perfect. Yeah. Krumiand. Hello, and thank you for following. Nia is cute VTuberes. Nia plus nacht. Nia. What is Nia? Is Nia the emotes that you're putting? Good night. What? Good night. Good Nia. I suppose. Yeah. If we are going to my memeish way of good night. Okay. Good night, bigger operator. I hope you have a good day. Well, good night, I suppose, if you're going to bed. But yeah. Here, when we're creating the StiVec, we simply need to say just create a StiVec, and I'm actually gonna call it StiVec type, so that I can easily just call this StiVec. StiVec type. We're gonna call this StiVec, and then it's just gonna have nothing, and then StiVec dot IDs is gonna be equal to malloc. Malloc, however, the size of a UN32 is. Times the amount of elements we want to switch's size, and then we do the same thing but for the elements. Right. This rather than the size, it's like the max size. So we apply the same thing here. So max size, and then here the same thing, max size. Perfect. Yay. And so, oh yeah, you're right. You're right. I didn't change files. What? Sorry about that. Yeah. What the hell? Anyways, there you go. That should be fine now. Perfect. So that's StiVec insert, which returns the UN32T. Well, no, that's not StiVec insert. That's create. Create StiVec. StiVec. There you go. And then you need to pass me the max size that you want. Perfect. And we malloc, so we need to include the standard library here. Perfect. Okay. So what are we gonna do next? Conflicting times for create StiVec. Why? The StiVec is the same. Oh, never mind. So now we need to insert. So for insertion, I'm gonna give you an ID back. So StiVec insert, it's gonna involve you telling me what it is that you want to insert. So this is the element that you want to insert. How do we do this? Well, we are going to. Yeah. So when we create the StiVec, we actually need to populate all of the IDs. So for int I is equal to 0, I is smaller than max size, and then plus I. I'm going to say StiVec, but IDs in position I is equal to I action. Perfect. We initialize them all, and then we finally return the StiVec that we've been talking about. When we insert into the StiVec, we are going to, of course, need to pass which StiVec we're talking about. And then what we do is we simply say, well, I guess the StiVec also needs a size. So here, we have 32T size. And of course, we initialize the size to be equal to 0. Whenever we insert at the end of it all, we're going to have to increase the size. So StiVec dot size assume, but then this needs to be a pointer to the StiVec. Perfect. That's at the end of everything. What we need to do is we need to insert something into it. Why not calloc 0 no garbage? You mean this? So we actually need to initialize this to be an ascending sequence of numbers. So what I'm trying to create right now is a stable index vector from scratch. I don't remember exactly how it works, but I think we can just figure it out. Like, yeah, we can just figure it out as we go. But yeah, so it's One alloc you can. I mean, I don't really care what this contains, right? Because it's I'm supposed to not care about what this is. And same for elements. So it doesn't really, doesn't really matter that much. When we insert into the Stevic, what do we want to do? We want to know what the size is and return what ID is at that size. Okay, perfect. So what I do now is go to stevic.ids, right? And then this is the ID that I want to return. So we're going to return Stevic IDs into the Stevic size and then decrease by 1. Yes. Perfect. And then here we simply say stevic.elements at the size position from stevic.size, stevic size. It's going to be equal to the element. Perfect. And I think that's exactly what it needs to do. Of course, we forgot to include the fact that we need to include a pointer to the Stevic. And this should be a pointer. Same here, where we have Stevic T star Stevic. Then finally Stevic T star Stevic. And then we grab an ID. I think that's all we need. Right? Yeah, I'm pretty sure. The extension is just low, yeah. For remove, we don't need to return anything, and then we do Stevic remove. And the Stevic, what it's gonna do is it's gonna grab a pointer to whatever Stevic we're talking about. To element. Well, not the element, the ID. And then what I do is I go into IDs, right? I obtain whatever. Ooh, okay, this one's gonna be difficult. Well, not difficult, but we need to think about it a little more. We go to the position specified by your ID, and then that's going to give the position. So we have 3050 plus, it's going to be this. So this is not the ID's element. This is more like the, well, I guess. I guess it is. Yeah, it is. Rockcards, welcome. We have the position, right? We obtain the position, and then what we do is we need to exchange the two elements. So temp, it's going to be equal to whatever is in the elements array at that given position. We need to exchange it with whoever is at the back of the Stevic. So Stevic's Stevic elements, and then we access whatever Stevic size is equal to Stevic elements at that position. No, sorry, it's the other way around. This guy needs to go here. So we need to transfer the last guy into here. So we swap them together. And we do the same for their IDs. So Stevic IDs at this position is going to be equal to, I guess then we need two temps. Temp element and then temp ID. TMP ID, which is equal to a Stevic of IDs inside of ID, which I guess is the position, right? So Stevic elements at this position is equal to this. So I don't really need this. Never mind. Perfect. And then we say this is equal to Stevic at elements at Stevic with IDs. Yeah, this should be IDs instead. And then once we've done this, we can exchange on the other side. We grab the elements of Stevic size and make it equal to TMP element. And then finally Stevic of IDs at the Stevic size. So it's gonna be equal to plus. So Chivadim, thank you for following. Yay. So once we have done all of that, we simply decrease the size and return. Right. I think this is the way. We have done run. Let me see. So suppose we have a something that looks like this. So 0, 1, 2, 3, right? And then it hosts the numbers, you know, the letters A, B, C, and D. So I'm gonna call remove. I'm gonna remove C. All right. So I'm gonna call remove 2. Then what is the position? So the position would be in IDs. So I want to remove 2. I'm gonna go here and then I'm gonna say, oh, it's this guy. So my position is position 2, since nothing in the array has moved. Then I'm gonna grab a temporary element. The temporary element is gonna be equal to whatever stored in there, which is C. Actually, there is no need for a temporary element. Never mind. Because we only need to do this, and then whatever is at size is gonna get lost either way. So we don't care about it. There you go. Okay, and then what we do is we simply swap C, which is the element we want to eliminate, with whatever is at the end of the array, right? So elements pos is going to be equal to whatever is at elements Stevix size. So this becomes a D. And then this line over here makes it so that the ID that's over the D becomes, you know, becomes whatever we need. But that shouldn't be... Let me think. Okay, now we change it for a 3 and then there's nothing. But what happens now if I try to delete B? So I'm trying to delete B and I enter elements. So for A, for example, right? I pass in Carl's dev, welcome. We're creating a stable index vector from scratch just for the sake of tests. And yeah, so we have here this guy. What if I pass in the ID 0? Then it's gonna compute the position. It's gonna say, yes, I know who you're talking about. Wait. Okay, yeah, and then, oh, no, that was important. That was important. This guy was important, right? Was it important? Yeah, I think it was important. Okay. So here when we exchange them, and then C, and then this becomes 2, what ends up happening is once I enter index, say I want to now eliminate D, then I'm going to enter index 2, 1, 2, then it's gonna tell me that D, what? Oh, yeah. 1, 2, and then 3. So I'm gonna discover this. I'm gonna go here. That's what position is gonna store. And then I wanna exchange, yeah, whatever is in that position and then change it. Okay, I think it's fine. How come are you making a memory allocator? Yeah, so we're making a memory allocator from scratch. This is not part of the memory allocator. This is part of sort of, it's a data structure that I want just in order to keep track of something for the tests. And so we're just taking a little detour of like around 20 minutes to create the data structure from scratch. Yeah. Why are you making it? Oh, it's for the sake of learning. We just want to learn how memory allocator works and, you know, how memory allocators work, how, you know, how do they do everything. So we're basically learning by doing, which is, yeah, in my opinion, the best way to learn. So yeah, that's why. And we're gonna try and make it performant after this, which I'm not sure we can easily do. But yeah, unit 32 pos is gonna be the Stevix ID's array. We simply enter the ID. And then we're just going to return whatever is stored at Stevec inside of elements for the pause. Yeah, I think that's the way. Perfect. And Stevec get needs to return a uint32. I think. Great. I think that's it. Right. Did we successfully create a Stevec? I don't know. It seems like it, but conflicting types for Stevec get. It's a uint32, it's called Stevec get. It accepts a pointer to the Stevec. It accepts an IDE. I think this thing is just hallucinating a little. Why are they conflicting types? Previous declaration is here. And then it gives me the exact same declaration I'm using. Hello? Refresh? Oh, the extension is just slow. Okay, I think that's right. This is exactly how a stable index vector can be implemented. Okay, sure. Now that we have this, we can just go in and instead of doing this, we are just going to grab the last one. So I guess I want to create a, uint32t. Oh, well, no, actually. Yeah, no. Let's not do that. We're just gonna go here and so oh my god, I'm all over the place, dude. Let me just create a different file, right? Test random.c. Yeah, because there's a lot of things in this file and I don't feel a little overwhelmed by it. Let me grab this. Okay, let's put it here. Perfect. Oh my god. Okay, we need to include the standard library. We need to also include the standard int definitions. We need to include our own file for MMH. We also need to include our own Stevec implementation. Perfect. That's fine. We also need to include for Assert. Perfect. Yay. What else? Nope. And then setup we do need to bring. Oh, we bring it for here. Oh, sorry. Need these three. So we're just gonna copy it here at the beginning. Perfect. And then I need to include time. Include time.h. Perfect. I think that works. Except for references to block. Yeah. So now we need to pick a block. So what I'm gonna do is I'm gonna create a Stevec t, right? I'm gonna call it free blocks. So no need to keep track of this. And then free blocks is gonna be equal to the creation of a Stevec of size 10 also, right? Because there can be at most 10 blocks. Now what we're gonna do is we're gonna say, okay, pick a random thing from the Stevec. So here what we're gonna say is we say, well, if, I guess, yeah, if the Stevec size, oh, okay, let me think. If free blocks dot size is equal to 10. Then we reduce I so that the loop doesn't end, and then we continue. A different way to see this, yeah, I think that's fine. And then when we call free, it means that the free block size is fine. And then here we just increase, we simply say free that block. What am I doing? What am I doing? What am I doing? Okay, yeah, I'm gonna pick a random one. So what I do is we go into the blocks array, and then we're going to pick something, right? Free blocks. So here from the Stevec, we get pos from the standard index vector. We just get some block that's free, right? Free blocks. And then after we get that block, so we're just gonna generate a random integer between never mind. Oh my god, wait. I'm so over the place. Like I don't know what I'm doing. Like I know what I'm doing, but I just need to really think about what we need to do. So the thing I want to do, right? Thing I want to do is to generate a bunch of random operations that are going to stress test our memory allocator. That's all. So what we do here is we're picking a random operation where 0 is malloc, 1 is free, and 2 is realloc. And then after that, which actually reminds me we need to do this. Then after that, oh, sorry, never mind. And then after that, what we do is we say, well, right, pick some random operation, 0 for malloc, 1 for free, 2 for realloc. If it's an alloc, then we just create a block. If it's a free, we free that block. And if it's a realloc, we realloc the block. Very good. The thing is, you can only call free in blocks that are already allocated. So we need to find a way to prevent double frees. Not only that, but for realloc, we need a way to, like the block you need to provide is a block that isn't free. So it's a block that has to be allocated. And thus we need to prevent, free blocks from being selected randomly. So what I was doing is I was keeping a stable index vector of blocks, right? I was just keeping track of a bunch of blocks. And then picking the free blocks from there and eliminating them once I use them. So just for the sake of, I don't know, simplifying our lives, I'm just gonna create a function called Stevec random. I kind of don't really care that much anymore about everything being the way it's supposed to be. So first of all, assert that the Stevec's size is greater or equal to 0. Yeah, okay. And then what we do now is, so now I need to include assert to grade, thank you. And also, did I include pragma once? Yes, I did. Okay. And so what ends up happening is I want to pick a random element from the standard index vector. What I'm going to end up doing is, so I guess we also need to include, oh my god, include time.h, time.h, time.h. Yeah, so we need to do srand and then time and then null when we create the Stevec. And then finally we just say rand modulo, I don't know, the size of the Stevec size +1 question mark. So this guy here in closing parentheses, and then we're just going to return that. Return the Stevec in its elements array, accessing just a random element. And in fact, I think it's better if you just provide an IDs. Stevec random ID. Perfect. I think that's fine. And then here I can just do, oh my god, BK pause. I can get a Stevec. Forgot to include that in the header file. Import ETT Stevec random ID. And all I do is say Stevec T, and then pass in the Stevec and make this a pointer. Perfect. So when we do, oh, okay, Stevec, dude, come on, random ID. Then I pass in the Stevec that I want. Come on. Okay. Stevec random ID. Then I pass in this. And then I just say Stevec get whatever that random ID is. Perfect. Ah, finally. There you go. And so now what we can do is we can enter that block position that it's been given to me. And we know that that block is not going to be free. So now we can pass whatever we want to it. It's a pointer, and then it's here. Okay, oh my god. Oh, finally. My god, that was a hell. And so now when we free them, so when we free a block, actually, why do I call it as free blocks? This is the allocated blocks. If this thing is equal to 0, then you need to increase I and continue. When you allocate a new block, you need to just make it so that alloc blocks, well, I guess Stevec insert into this specific one, alloc blocks. Insert into the allocated blocks the block that you just allocated. And plus no blocks. Perfect. Okay. Should we insert the index instead? Yeah. Then here, alloc blocks.size equals 0. Perfect. And then we continue. If this happens, then we need to get alloc blocks and then a Stevec random ID. So we obtain a block which is allocated. And then once we get that block position, we need to remove it from the Stevec. So Stevec remove. And then I pass in the alloc blocks Stevec. And then take it to be the one with ID VK pos. Right. I think so. Yeah. So instead of BK pos, maybe I can do like block ID. Oh, I see. The block ID is this one, and the block position is this one. And here, un.t bkpos is going to be equal to static get, and then I paste in that. Stevik get whatever the BK ID is. Great. Okay. Oh, okay. And then we put in the BK pulse. Hopefully it works. If it doesn't work, I am going to commit a crime. I am going to commit a crime if it doesn't work. Because it's just so annoying. Let me see. We pick a random operation. We perform that operation. So here we insert it to the allocated blocks, if that's the case. Otherwise, we pick a random allocated block, right? Allocated block set size, the block ID, and the block position. Uh-huh. And we have a little block. I think we're fine. Great. Okay. Let's try and run this and not die while we attempt it. Make file. I don't know if I do test random. We can just compile libc mmc arbitrary.c and then test random.c, and then we just use the exact same flags over here. Perfect. So now we make test random. What? Undefined symbol for architecture. Oh, of course. I need to include those in the make file too. Oof, okay. Okay, that's a good sign. Okay, it seems to compile. Boom, segmentation fault. Okay, sorry. /bins/ test random. Oh. Are we fuzzing yet? So we're kind of fuzzing. I'm trying to create that, right? I'm trying to create like some sort of random tester. Something that just picks a random operation and performs it. It like picks a random operation and says, okay, if it's an alloc, then just allocate some block. And then if it's free that block. If it's realloc, reallocate that block. And the sizes are also random. Like everything is just random. So it sort of behaves like a fuzzer of sorts. The problem is like getting it to work since C doesn't have containers. It's like very annoying because we just had to create our own container. And so now when I run it, it just stays static, allocating 256 bytes, and then it just does nothing. So I don't know what it is. Why is it behaving this way? Don't know. Don't ask me. Because it's like extremely annoying. Random. Okay, what happens if we run this the way it is right now? My back hurts. We've been sitting here all day. Please, okay, gods, the gods of programming or whatever, they can spare our lives for once. Because notice we num blocks, right, and then we create the Stevik, the standard index vector. So we go here, right? I is equal to 0, and then the operation that we perform is 0. So then we allocate some sort of block. Take a look at the debug console, right? and then it just stays there. So what is create block doing? It's not doing anything that requires sleep system. Okay, really good, penguin operator. You know, but we have a huge problem here because what? Like this doesn't loop. Nothing loops here. Nothing loops here. The only thing that loops is nalog. Like potentially. Are we just looping on nalog? Like, is our implementation just wrong and we just discovered it? Like, I don't know what to tell you. I don't know what to tell you. Make test random. Okay, let's run this. F5. Brother. Okay, so we do malloc by minute, and then we enter the tests, and we enter test one, right? Then there you go. So we create the StevEc, we create an operation, and that operation is 0 again. Then we create a block. So first of all, we create the random number. It seems like the random number is some random number. The size is 145, right? So now we create the data, which should not loop. Then we enter nalog, and we loop inside of nalog. But the logs are not saying anything. They just say allocating 152 bytes. Where are we stopping? Oh, not this again, please. Oh, please. Please. I'm gonna. Oh, wait. Wait. I think I know what it is. Oh, we forgot to initialize the memory manager. And a minute. Dude, okay. Yeah, I hate my Chunkle's life and whatever comes after that. Let's just run the terminal. Let's go. And then let's run it. Now it should work. Why make not GCC maybe better log and make file support? Wait, what do you mean? What is the question? So we just have a make because it's a little bit more organized, right? Yeah. I'm gonna enter this function. Okay, now it should work. Enter here. Then create a random operation. Please don't tell me it's 0. Dude, it's supposed to be random. It's supposed to be random. Why are you generating this? Because what? Anyways, yeah, make file is for instructions, right? Yeah. It's for like, tell it what to do. And in this case, we just call GCC through it, but it's just a little more organized. Let's see what happens. We create a block, which should not take eternity. Why? There is some block that we are accessing that is just completely void. Like, wait, but when we create a block, we're calling malloc for the first time. So what are you saying? What are you saying, brother? What are you saying? Are we using the same bean? Yes, we are. Okay. Let's calm down and let's run this. And let's go step by step of why this thing is so stupid that it's locking. Okay, test one. Then create the StevEc. Yeah, sure. Random is gonna be 0. Oh, it's 1 for once. Then it's gonna enter here, but it's gonna continue. I need to, okay, the moment I need this to generate a 0, it doesn't. Can you generate a 0, please? Can you please generate a 0? Brother. 1. Okay, generate a 0. Dude, what happened? 2. Oh. 2 again? 0, finally, okay. So we enter here, and when we try to create the block, we continue, blah, 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 we create a block. We create random many bytes, then we enter malloc. Let's see what happens. So, dude, why was my thing formatted like this? Why are the things in the new... Oh, this is so ugly. No, what happened? My entire thing got ruined by the formatter. Anyways, we enter... What? Why are we not entering the first allocation? Oh my god. What am I doing wrong? Wait, I'm a minute. Oh my god. Wait, I had written this down before, right? Oh, but I had written in the wrong file. Anyways, oh no. Okay. brother, please. Brother, please. Work. Okay. We're going to be professional and not enter panic. Please generate a 0. 2. Okay. Okay, this thing is really training me. Please generate a 0. 1. Generate a 0. 2. Okay. 2 again. Oh my god. 0, finally, okay. So we enter here. And when we create a block, we should be able to see everything flow so smoothly. So smoothly. Enter, enter. Yes, perfect, perfect. So we return that block, and then we say, well, the first index is going to be this. Then we Stevec insert the new thing. We increase the amount of blocks, and we continue. Okay, so we allocated something. The console should say, yeah, heap expanded by this much. Then we're going to do something random again. We're going to reallocate some block. So here it should be able to pick a random allocated block. The BKID should be 0, right? And then the Stevec get should give us the block at position 0. Yes, we remove that, and then we use that block, and then we reallocate it. And we reallocate the block, so we should see in the logs that it reallocs. Reallocs, yeah, reallocated 24 to 126 to 176, sorry. And then we continue. I is now 2. Now we generate a random operation, which is going to be allocate another block. Literally omnipresent. Yeah. Yeah, Penguin Operator is like everywhere in every single stream of like every streamer when it comes to programming. It's so funny, but yeah. And then over here we're gonna allocate something. So then we create that block, right? And we should be able to flow through this with no problems. The logs are fine. Then we insert it into the Stevec, and it should have received ID 0, if I remember correctly. So now we continue. Yeah, okay. Now we pick another random operation. We're going to do a realloc again. So we skip this. We know that there is something. The BKID should be 0. Ooh, it's 1. Okay, but the BK pause should also be 1. Wait, what just happened? Why is the BK ID 1? Wait, now I need to inspect the Stevek. Because what the hell is happening? Why is the Stevek behaving like that? Huh? I mean, I guess so. Like, wait, there's something wrong with the Stevek. Stevek, are you here? Okay, let's see. So if we grab Stevek, we create the Stevek, we do all of this, then we go through each and we assign a bunch of IDs. When we insert something, we insert it at Stevek size, right? So the Stevek elements at size is going to equal to the element. Yes, we increase the size, and then we return Stevek IDs at the size minus 1. Yes. Oh, okay. This needs to exchange with the last element of the vector, so it's size minus 1, not size. Okay, that makes sense why. Okay, perfect. Yay, I think we did it. I've heard it lives down or read it somewhere. Okay, size minus 1. Then we create the IDs. Whew, perfect. So now we make again. Now. Okay. We stop this, we make again, and then we run. We debug to see if the fuzzer is working correctly, if you can even call this a fuzzer. It's just a random test generator. And we do this, we enter this, we enter that. We initialize, we continue. So let's see, first operation, it's a free. Sorry, it's a realloc, no. Until we generate a 0. Please, 1, no. Please give me a 0. 0, okay, perfect. Fuzz input is the random seed. Yeah, exactly. I'm just testing that, like, the action of performing random operations is actually correct. Like, it actually does random things, and, like, it's keeping track of things as it should. So here we allocate a block, right? So see, like, it's just generating a random in between 0 and 2, and that is the operation. So if the operation was 0, then create a block, insert it into the Stevek to keep track of which blocks are allocated in. Because we need the Stevek standing for standard index vector. Sorry, not standard, stable index vector. We needed to keep track of if the operation is a free or it's a realloc. These operations cannot be done on free blocks. So we have to keep track of which blocks are allocated. And because of that, we just need to, insert. Yeah, I follow currently 70 people on Twitch. What? Damn. It's just, you just are everywhere. Anyways, that's interesting. Damn. Yeah. Wildflower things to say. But yeah. Anyways, num-blocks are these, and then we continue. And then here we pick another random operation. So what operation will it be? It'll be another allocation. And so now we create the block, and then we insert it, and then we continue. So now we have 2 blocks for now. We create another operation, which is a 1, which is a free. So now it should pick between the 2 blocks that we have. It'll pick one of their. Just software and game development category, you're following 70 people? Damn. Okay. Anyways. We have these 2 blocks that we need to decide on. And so we're gonna go here, right? And we That's all of the people in the category. Yeah, yeah, basically. So here we have these two things, right? We skip this, and then we're gonna grab a random one. We're gonna grab either block 0 or block 1. So BKD should be 0 or 1. It's 0, so BK pos should be 0. Yes. Then we remove that from the STVEC. So only block 1 is left. We grab that block, and then we free it. Yeah, and the logs are fine, right? The logs are saying, oh, this has been freed. Then we reallocate. Well, no, sorry, we don't do anything. And now we need the next operation. It's gonna be another allocation. So then we allocate. And when we allocate, it is going to inherit the index 0. So both index 0 and index 1 are now at play. And so we now pick a random operation, right? That operation is realloc. So now we're going to go here, and then we're going to pick a random between 0 and 1, because they're the only available. So BKID is either 0 or 1. 1. So BK pos should be 1. Yes. And then we remove it from the STVEC, so now 0 is remaining. We go to realloc, and then we reallocate it, and then we should see that in the logs. Perfect. Then we continue. We create another operation. It's going to be another allocation. So you're going to live in index. Your ID is 1 and your block index 3. If I'm not mistaken. Yeah, your block index 3. Okay, so ID 0 is the second block. ID 1 is the third block. Remember that. So we create another operation, and it's going to be a realloc. So now we go to the realloc, and then we pick a random one between 0 and 1 for the ID. What? 2? Huh? What do you mean 2? We've only had 2 IDs max. So 2 should be out of the game. Did I miss a block? And then BK pos should fail or something like that. 0. Okay. Well, never mind. Okay. Because wait, block 0 is not even free. Sorry, block 0 was freed, no? Oh, wait. Wait. We only remove if this thing is freed. Oh, okay. Yeah, this only stops being allocated if it's freed. Otherwise, it just stays in the game. Okay, anyways. Reset. Make test. Run again. Let's verify that the Fuzzer is doing what it's supposed to do. And I'm absolutely not interested in gaming. If I watch someone gaming, that's only if they stream some coding content. Interesting. Yeah, so pretty good. We go E2E tests, E2E test 1, and a minute. Then we continue, we create a STVEC, we go on, then we create an operation. We're gonna realloc, but there are no available blocks. So we continue, we try to perform another operation. By the way, do you know who is Sodding? I don't know Sodding. I only know Mr. Sozin. Yeah, of course. We generate another operation, and it's gonna be this thing, and then we skip, and then 0. Because I remember when people asked, when I mentioned sorting, and then somebody said Mr. Sosin, and then I didn't make the connection. I was like, oh wait, never mind. Yeah, it was like in one of our earlier streams, like a few days ago. Anyways, We generate another operation, which is going to be a 1. We still don't have blocks, so no. Please generate a 0 for the operation. Please. Please. 0, finally. Okay. Don't know who's. No. I said I don't know sorry. I only know Mr. Sozin. Like, yeah, Mr. Sozin. Hello, everyone, and welcome to another recreational program session with Mr. Sozin. Yeah, check him out. Yeah, a very underground, beatboxer. Anyways, we're gonna have. Yeah, I know it's Russian. So we're gonna do an analog here, and we're gonna create a block. So this is the first block ever. It's gonna be ID 0 and index 0. Hey, you are the profit guy. Penguin operator or me? Either way, it works. Well, really, yeah. We insert, we continue. So we have only block 0, index 0, right? Then here we create the operation, and we want to reallocate. The only block we have is ID 0, position 0. So BKID should be 0. Dude, what? What? What is happening? What is happening? Why is this behaving this way? Why is it not supposed to be behaving this way? Like IDs. What is going on? Oh shoot! There shouldn't be a +1 here. Who introduced that +1? That only an idiot would introduce a +1 over there. Yeah, that's what was messing up with everything. All right, people. Once again, I'm so sorry. Guys, I suffer the same amount as you. Don't worry. Oh, we got a 0 first. Let's go. So we allocate a block, and this is gonna be block 0, and its ID is 0. Then the next operation is gonna be another allocation. Let's go. This is gonna be block 1. Index 1, ID 1. Then we're gonna do. Hey, you are the money guy. Like, do you respond? Wait, what do you mean? Do you respond? Like, do I respond? Should I respond? So, I'm not sure. Does C accept name.name pointer, or is it strictly for pointers? It's strictly arrow. For like things you actually have is strictly point. So yeah. Up and then okay. The operation is a free, so either 0 or 1. Any responders in chat? Wait, what do you mean? What is, guys, what are we responding to? Sorry, I don't know what. Huh? Wait. Anyways, this thing here. Like, if you mean when we were doing the makefile and we were like, GCC profit goes up. Yeah, this is that stream. But yeah. Yeah, what did you mean? What did you mean? Sorry, sorry to with the money thing. Did you mean the makefile? If so, yeah. Okay. So we're going to perform roast part. We're going to perform a free. We're going to perform a free. So we should skip. BKID should be between 0 and 1. Yes, 1. And so the position should be 1. Yes, it's 1. It's 1. I don't know what's happening. Okay, wait, guys. Do we have a lot of delay? Because like there's so many things like like Smart is saying like some random thing, and then I try to respond, but I don't know if that's what you mean. Smart is right. Anyways, right? So here we get that, and then we free that block. So block 1 is gone, the same as index 1. Mental clarity. What does mental clarity mean, bro? What does mental clarity mean? What? These are some like Riddler phrases. Why are we? Anyways, create another operation, allocate another block. This is gonna be block number 2 inside of index 1. So index 1, block 2. Joel, I I am going to stop. Uh, I can't cue the ASCII tour. Ooh, interesting. I don't know. I didn't know there was an ASCII tour. What were we doing? Oh yeah. Wait. Okay. I'm gonna focus on this so that we can debug and don't end up with errors. Block 2 in index 1, and then block 0 in index 0. Next operation, a free. So then we go here and then we generate either ID 1 or 0. The ID is 0, so the position should be 0. Oh shoot, I clicked the wrong button. Well, anyways. Okay, it seems like nothing bad happened. So that's great, I suppose. How about we do 100 things? Um, yeah. Streamer not off today with a category. Yeah. Like I've been trying to go to a bunch of streams and stuff. Like mainly I've seen the Ferrari streams because I wake up really early, and in that time is where I try and watch some other streams. And the Ferrari is usually streaming at that time. But yeah, gotta explore a little more on my side. Um, okay, let's recompile, and then let's do F5 to run the debugger because it's the greatest debug, the greatest fuzzer of all time. Oh shoot, we got an assert problem. Oh wait, you know what we should do? 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 Wait. Don't let this idea escape my mind. We should generate. Okay. So instead of creating the logs from the program, we don't do that. And instead, we make test random. Oh, what the hell? Oh, the data got corrupted. The data got corrupted somewhere. Damn, that's crazy. Okay. So what we're going to do is we should make a log of all the things that we've been trying out. So here I should do something like printf, so that if we ever fail an assertion, we are able to recreate the steps that got us to that failure. Let me see. AKA developed from scratch. Yeah. You on US specific? Yes. Do you know about the Ferrari's views on AI? Not really, because I've only watched one of the Ferrari streams. I think it was yesterday that I got the chance to catch him when he was streaming. Did you manage to get a blue screen yet? I heard that it's actually possible in C. Really? Not yet. Oh, awesome. Yeah. I am from Colombia, but I'm currently in the US. So I am currently in US Pacific time. Print random seed first. Helos AI. Oh, really? I see. But yeah. All right. So the thing is, what do we need? What do we need? And I think as far as I know, he very hits it. Yeah, I imagine. It's a reasonable position, definitely. I would very much support him on that. Seed. So then we get a seed. And then when we initialize, Actually, Mr. Stevek, do you do some sort of weird thing? Yes, you do. Let's not do that, please. Perfect, thank you. And so what we're going to do is we're going to go to the test. We pass in the seed, or well, it will be a size t, right? We pass in the seed, and then when we call this, we generate a seed over here. Wait, how do we current? Oh wait, I guess that's stupid, right? Because the seed is whatever time has. Seed is equal to time and then null, right? Right? Yeah, and so the seed is whatever we pass to srand to seed the random number generator. And then we tell the end-to-end test what the seed we used was, following the indication of Vicente de Lencar. And then, wait. Okay, I was so confused, lol. I was like, there's no way Colombia is 3:41 p.m. Yeah. As far as I know, he verified AI. He's Venezuelan. Wait, who is Venezuelan? Is the Ferrari Venezuelan? What? I thought he lived in Europe. The Ferrari is Venezuelan? Dude, you're kidding. What? Dude, that's insane. That's insane. Let's go. Latin America. Wait, I didn't know that. I didn't know that. Wait, that's amazing. Pretty good. But yeah, excellent. So I don't know, printf. We want to print whatever the seed is. So then we say seed, and then we do percent ulong, and then we pass in the seed. We of course need a new line. Dude, come on. What do I need then? Oh my god, zoo? Do I need zoo? I need zoo. Okay. Here we're going to print malloc, and then we're mallocing what? We're mallocing this size, this whatever. Actually, what am I talking about? I don't need to print that if I'm printing the seed, because I'm gonna know what the seed is. Anyways, stop, right? Reset. And then let's just run it. Let's just run it. Okay. We get a problem. It's no longer a valid block. Notice how big the heap is by this point. It's like 1744. It's absolutely insane. The seed is this one. So what is it that we do? So I do want to introduce maybe some things here, right? Printf a malloc, right? Malloc on the number of operations. So I want to keep track of how many operations we have performed. So ops is equal to 0. And then I just increase this. So plus ops. Then I do printf malloc free. And then I do plus ops. And of course the new line. Then a new line. Plus ops. And then printf. And I do free. f3 slash, oh no, this is not f3, this is a realloc slash n and then plus ops. Oh my god, okay. And then every single time I just do this. It's actually a UD. Oh, sorry, D is correct. Free, and then we append the thing that we need. It's gonna be ops, and then malloc %d, which is gonna be ops. Okay, perfect. We run make again, and now we run the guy, the fuzzer. So let's run the fuzzer, and hopefully we'll be able to see in the console what happens. Ooh, we performed 18 operations and then a bad access. So wait, the fuzzer is absolutely incredible, dude. Every time we run it, we discover a new bug. So thank God we spent time on looking at this. I was arguing with him about that because I see being anti-AI is right wing, whilst anti-AIists are somewhat supposed to be left one. It's a nice moment. I just me eat him. I want to shoot you up. And got banned from Twitch for 31 days. I don't know. I mean, I wouldn't have. I don't think the position related to pro AI anti AI is right wing or left wing. It is. I feel an issue that it's a little bit more overall general, right? I feel I'm a little more anti AI. I would like to think, but yeah, interesting. So we have the seed. We have the seed that makes the whole problem appear. So let's do that. Let's do that. Let's grab the seed and use it here. So now I suppose if we run it again, to all the people that motivated me to do the fuzzer, thank you so much. I was losing so much hope, but it seems like it's working now. Unless it's our test file that is actually the one that's wrong. Because it very much could be the case. Especially the Stevec. The Stevec is like, okay, no, it generates the same problem. Great. Okay, let's run this. Let's run these. Okay, so we run the setup. Well deserved ban, says JW01. Hello. Okay, let's see. E2E tests. That was at spring of this year. No. Okay. Let's enter here and let's see what happens, right? Let's follow this step by step. So first, this one's gonna be a long one. So you're gonna have to keep track. We're gonna have to keep track of the allocated blocks. Okay, let's see what happens. So we pick a random operation. And I think we're gonna need help of the Excali draw to draw exactly what's going. Well, actually, we can write it here in a comment. Okay? Get ready to monitor the state of the heap. And this one's gonna be long. It's gonna be like 40 minutes in a single case. Okay. First operation. Yeah, that's not that helpful because we skip it. Next operation. We skip it too. Sorry. Next operation. Okay, an allocation. Perfect. And what do we do with that allocation? So let me actually write it down somewhere. So I'm gonna grab the Stevec file. I'm gonna put it here. Actually, no. Okay. We have an allocation, right? What is the size of that allocation? So we put it in block 0. So blocks 0, it's gonna be right? Something that is 157 wide. So blocks 0, 157, right? That's gonna be our first thing, and it's allocated, right? Great. And the data is just a bunch of ones. Perfect. So this is a one. Let's continue. So that's our first operation. Then, next operation. Let's see. It's a 0, so we allocate another thing. Then we continue. Then we create a block. Let's take a look at what that block is. It's 102. So then we do this, block 1, 102, and then 2 in size. Actually, I don't think I need to do this. That's fine. Perfect. So then we continue. We continue. Perfect. Then we pick a random operation. That operation is going to be a 3. So then we go here. Then we pick that block, which should be one of the two. It chooses block 0. So freeze block 0. I feel I should be writing down the order of operations that we see. So we first are mallocing. Well, there's no need to do that. Yeah, never mind. Where are we? We're here. So it should get block number 0. Yeah, and so it frees block number 0. Okay, so block 0, bye-bye. Block 0 is just there, and now it's freed, right? Now it's freed. Which I'm not sure how we could symbolize it. Maybe with, how do you symbolize freedom? Maybe with 2 bars. I don't know. Yeah, let's put it just 2 bars. Let's continue. So now we do another operation, which is another allocation. And then we allocate. We allocate a block, which is block number 2, of size 176. So block 2 is of size 176. Then we continue. Pick a random operation. This time it's going to be another allocation. We allocate another block, right? So now that block is going to be block number 3, which is allocated, and it's 132. Now we continue. And then the operation that we chose is another allocation. Whoa, whoa, whoa. Okay. See, insert. And then that allocation is number 4, I think. So data size, which should be 71. Okay, then it's allocated. So 71 is before 71. Great. Now we continue. Pick another operation. This time is a free. So which one are you going to free? We're going to free specific random ID. So the block position is 2. Okay, perfect. Oh, sorry. Maybe it's sufficient. You libertarian. Easy to figure out. I am the we live in a society dude. Okay, so we enter the operation, and then we're gonna try and free the block in position 2. So block 2 is gonna get freed. So say bye-bye block 2. Then we free block 2. Right, 176. 176 indeed, block 2. And we skip it. Perfect, so block 2 now gets freed. So now we continue. We pick a random operation, that one being a realloc. So we go here and we choose a block to reallocate, which in this case is block number 3. So B3, it's going to get reallocated. And we have to be careful on what the size is going to be of the reallocation. And we actually don't know, which is a huge mistake. Yeah, I should have. Oh no, all of this for nothing, because I need to know what the value of the variable is. Let's see, we try to reallocate, and we try and do this with block 3. Maybe I can step into the function call? No? No, I don't think so. Yeah, okay, yeah, I lose track because now I don't know the size of the reallocation. It's okay. So here you have 33. Size is going to be equal to randint, and then this thing, and size. Reset, then we do this, make plus random. Perfect. We continue. Okay, I think this was the state until that first realloc, so I think we can just skip all of this and wait until we reach I equals 7. Okay, I'm just gonna 3, 4, 5, 6, and then the 7th one is gonna be, yeah, so this is a free for 176, yeah, block 2, and then we have the realloc for block 3 here. Perfect, realloc. Then now we try to reallocate block 3 to something that has size 223. Ooh, that's a lot. So what that means is that we know the heap looks like this at step right before starting, like right after step 6, right? So the way it's gonna look at step 7 is we reallocate block 3 to be in something that's 223 wide. There is no such block, and so we're gonna have to expand the heap to accommodate block 3 into a 223 wide block. And so this block 3 is there, and this is now, you know, completely freed. So B3, this just is free. Nobody knows what's there. So what do we do now? What do we do now? We proceed to what? To reallocate, right? So we should see the heap expand. So if we go to the watch, we should see mem heap size increase. Yeah, when we reallocate the block, we should see it increase. Yeah, to 196. Okay. Then we do I is 8 now. Oh, I think that keeping track of it through the comments is really bad. The operation is 0. And now we print malloc. So we're gonna allocate a new block. We're gonna increase the operations. And then that block is gonna be block number 5. Because numblocks is 5 right now. Yeah, block 5. And let's see what happens with block 5. So block 5 is of size 113. So notice that block 0 is free. This space over here is free. And so block 5 is going to occupy it. Actually, no. This space is better for block 5. So block 5 is going to be here. It's going to make 132, right? Yeah. So block 5 is going to be 132. Um, no, this is really bad. This is really bad, guys. This is really bad. Oh my god. Ah, you know why? Because here the size of the first block is says it's 120, but it actually is 157. Ah, ah, no, no. Oh no. Okay, I'm losing hope. I'm losing hope. Ah, let me read the chat instead. Let's see. Oh, what the? Whoa, whoa, whoa! There's a bunch of stuff. What the? Society, dude. What do you believe? Communism and fascism are the same. Oh, okay, see, these are more politics. It's all a joke. XDDing. Hola, parcero. Hola, spacekibbutz.com. It switches between the different presidents. Okay, I see. Now let's talk about politics. Yeah. No. No, 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 no. Okay. Okay, I think we're gonna have to use the memory inspector. I'm sorry I had to come to this way. Um, actually. Let's think of a vibrant afternoon, like the one we're having here. What is the thing that we should do? I know. We should create a heap printer. Something that prints out the state of the heap every single time a function is called. What do you think? Yeah, I think so too. I agree with you. You're so brilliant. Okay. 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 Oh my god. I am. My back is like really hurting. Me. Okay, we're gonna create a heap printer, guys. We're gonna create a heap printer. I didn't want to get to this instance, but we need to. A heap printer. Okay. Okay, this is the last thing I'm gonna do today. If it doesn't work with the heap printer, yeah, a dumper, like I'm just leaving it behind. Like I don't. Anyways, we're gonna go to MM. We're gonna go here. And we're gonna add a debugging section. Void print heap. So when it comes to printing the heap, we just want to do things very simply. And then after that, so what we want to do is we want to start at the beginning of everything, right? So how do we start with it? Let me read the chat. Strong suggestion. Go to the wash your hands and face, then drink water, then come back. Yeah. Heat visualizer would be even better at some point. Yeah, but like I mean, we have a technically like a heat visual. We have a view into memory. If we could render the blocks, sure, but I feel that would be like too big of a project to put as just a debugging tool. Print 1000 bits. Yeah, base address. Okay, let's do this. I'm gonna stand up for like 2 minutes. I'll attend to my recommendation, and I'll be back in like 2 minutes. Okay. Yeah. Who's ready? Who's ready to tackle the problem? Who's ready? Who has the energy? We have the energy. We have the energy to tackle the problem. Let's go. Let's go. We can do this. Okay. Um. Anyone know why he's making a memory allocator? Just for the sake of learning. Just for the sake of learning. Since we moved away from the poly Doom Talk, let's move to the AI Doom Talk. Let's go! Let's go, dude! Let's go! Let's go! Let's go! Okay. We need to print a heap. What is the first thing that you need to print a heap? Well, we need to skip the ghost node. Great observation, brother. Great observation. So the thing we want to do is we want to have this print heap thing, and then we want to implement it inside of mm.c. And we're going to implement it, I guess, under the block member variables because we're going to need them, and the block neighbors. So over here, we're going to have something like, debugging section. Then we're going to say void print the heap. We're going to print the heap. So what do you need to print the heap? Well, we're going to need to skip the ghost node. So we're going to have a heap pointer to the current block, right? So the current block is going to be 0. And in fact, it's not 0. It should be equal to the padding. Then what we do is we skip the ghost node, right? And so we simply just say current block is going to be equal to the next block from this block. So skip the ghost node. And what are we going to do? We're going to print, in fact, so while current block is different from a no heap pointer, we're simply going to print to, you know, the console. We're gonna print a little block, right? We're gonna print something like this. Like what? Here, right? This guy, and then this guy. And then we should print inside of them the name of the block, which, well, there's no really such thing. We can only know the size of the block. That's like the main thing that we can worry about. Other than the size of the block, what else do we need? Well, not much else, right? The size of the block, whether or not it's free, right? Which I guess depends on what it is that we want to do. So maybe we do this, then we do something like this. So these are the block boundaries, right? These guys. Oh, wait, I think there's no string concatenation in C. Wait, how do you concatenate strings in C then? What? So how do I? Okay, let's do it this way. Let's do it this way. So, right, print. What are we gonna do? If the block is free, if the current block is free, then we're gonna have to print it. We're going to print it just as like a normal guy, right? 1, 2, %B, 1, 2. Perfect. I don't know why it adds the dots. Oh my god. Yeah, there you go. Right? And then what we pass in is gonna be the size of the block size of the current block. If it is otherwise, you know, like that, then we're gonna print the thing but with a different style. It's gonna be like this. This is what an allocated block looks like, right? Perfect. And then we do BK size of the current block. Perfect. And that way we print the entire heap. Because by the time we reach the end, we get everything, right? Okay, yeah, perfect. Can I create a memory allocator for your memory allocator? Sure. That would be like kmalloc. But yeah. And okay. New line. Wait, no. No. We don't want a new line here because I want to print them like in sequence so that you can see it like as if it was the actual heap. Right? So you like print them in sequence. And then we print a new line after that. If that's what you're referring to, then yeah, sure. For sure we need that. Okay. So now we reset. And then we make again. Guys, is this it? It is glory. So let's see. Let's print the heap after every operation. So let's do nalloc. And then let's print the heap at the end. Oh my god, the formatter changed all of my keys. Absolutely insane. I don't know why I did this. This looks so bad. Okay, let's go to nalloc and let's find all the places where we return. So we return here. So let's do print heap over here, print heap. Then let's go to the next return. I don't care about that. I care about this other one. There you go, print heap. Print heap. Yes. Then with end-free, we need to return, and we only return at the end, so we print the heap too. Then we, on realloc, we also return early sometimes. So here we print the heap, and then after that, we return early again, so we print the heap again. There's one last time where we return early. Here. So then we print the heap over here. And then over here, we also return early. Yeah, we also return early. So we print the heap again. And then finally here, we print the heap, but there's no need because end-free is going to make it so that, yeah. Okay, perfect. Let's make this. And then I think that we can actually just run it and see what the output is. What? Oh no. Okay, our print function is LGTM. What is, wait. Oh, looks good to me. Okay. Good. It's a problem. It's a problem. Our print function is not stopping. Oh, of course, because we never changed the next block. Oh my god, dude. We need to do current block is equal to the next block. Of course. Missing a B in the middle of the hitchman. Okay. Perfect. We reset. We make again. Ooh, we have a beautiful print. Wait, is this it? Is this what we wanted? Actually, I don't like the keys. I hate the keys. That looks so bad. Let's do it like this. Yeah, there you go. This looks way better. Hey, yeah, exactly. That's what I'm talking about. Okay, 1 1 and then 1 1 1. Yeah, perfect. Reset. Make. Reset. Print. Okay, let's see what's going on. So, oh, this is so good, bro. This is so good. This is exactly what we needed. Dude, come on. Okay. So what we're gonna do is not only maybe not the operation. Let's do malloc and then specify what it is that we allocate. Oh my god, this is so good. Let's go. Okay, so %d, we're gonna pass the operation number to know which operation this is, and then we need to know the parameters to malloc. So I guess we do here the unit32t size, which is equal to the random int. Add attach and harmony. Okay, size. Perfect. And so now when we do this, we print it. And then for free, we need to pass in what the parameter is, right? And then we change in this guy over here. Guys, I think this is the Renaissance. This is the Renaissance. We We have revived like the phoenix bird. And so now we need to say which block it is that we are currently occupying, right? I guess. I'm not sure. Well, not really. Well, well, well. Well, well, well. Okay, I guess we can just do something like char star mem heap low, and then obtain what this block's pointer is. Block.main pointer minus that. And then to whatever this is, add attach and harmony. And so now we have that, and that we convert to a unit PTRT. And then we're gonna know where the offset is, but then we need to subtract the size of an allocated block header to know where the actual block pointer is. And so we have that. Awesome. More than perfect. Okay, I think that's it. UL, is that what you want? C extension? Oh my god, the Z extension is gonna kill me. It is going to kill me. I want that right now. What is going on? Ah. Ah. How am I supposed to solve that? It's just zoo? Okay. Anyways. Whoa, whoa, whoa. What are you guys talking about? I've done it in politics. Yeah, in politics, guys. In politics. Any governance known to mankind always failed. Okay. Lived happily ever after. Okay, guys. Okay. Control. We're here for the coding. Okay. Yeah. Okay. So something. Okay. We do the %v and we realloc. And then what do we realloc? Well, we're gonna realloc. We're gonna say which block it is and then the size. So we pass in ops, then we pass in the same thing here. And then we pass in size. There you go. Perfect. More than perfect. Okay. Reset. Make. Run. Okay. So, what are we doing? The heap looks like this. So it's doing, we malloc 157, right? If you value your strategy. Hot but interesting. Sharif, what about dedicating some time for some discussions on South American politics? I'm not sure if the odds would be right. I feel like it did. I'm not sure if you guys would be interested in even hearing that at the beginning. And yeah, I feel like I prefer to keep the streams more neutral for everybody to enjoy. So yeah, it's also possibly let's focus on the memory allocator, guys. So what we have over here is a malloc 157. So we create this block of 160. That's good. right? Then we malloc 102, and then seems fine. Then we free block 24, which should be this guy. We malloc 176 of size, which should be this much. Perfect. Then we malloc 132. So where do we put the 132? We put it here in the 160. We split this block to put 136, and then we separate it into 16. And that seems correct. Then we allocate 71. So the heap expands by a given amount, and out of that amount, we split it and provide the 72, right? Oh, we're having a segmentation fault. Oh, shoot, I think I know why. To what value do these things add up? 128 plus 24 to 104 plus 136. That's already in the 360s. 500 and something. Do these values add to more than 1024? Is that the reason why? Because we're only allocating 1 megabyte for the maximum amount of things in the heap. 128 plus 24 plus 104 plus 136 plus 32 plus 16 plus 48 plus 232 plus 128 plus 64 plus 192. Yeah, that is the problem. That is the problem. Oh no. Okay, so we need more memory. 496. Let's dedicate 4 kilobytes to this thing. Okay. Yeah. I don't have that money. Let's see. So, guys, stop. Please stop. What's the name? Agitating penguin operator. There you go. But stop, please. Stop the discussion. It's okay. We'll have potential maybe in the future. I don't know. It's not in my plans to do that, but like, relax, calm down. It's so funny. It's like I remember that when in the World Cup when Spain and Argentina faced each other. There was this very funny video where Lamine Yamal, one of Spain's players, was like praying in the ground, like, "Oh, thank you, God," or whatever. Was praying because they won the World Cup. And then in the background, you can see the Spain and the Argentina players like hitting each other. So it feels like the same because I like look at the memory allocator and then immediately as I turn to chat, I see like some random discussion. I love hot debates. Yeah, me too. Me too. Well, like I've been trying to keep it more friendly and simple. But yeah, I think the reason is we ran out of memory, and that's all. Yeah, so now we fail the actual assertion after 31 operations. After 31 operations? Brother, what is this? 31 operations? What is going on? Your vector has capacity 10, by the way. Oh, is that it? Oh my god, Vicente de Alencar has come here to save the day, bro. Oh my god, that's probably the issue. Never mind, that was not the issue. Well, Vicente. Anyways. But yeah, uh, I don't know. 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 Wait, you get turned on. Dude, okay, Space keep beat. Please don't say these type of things. Just guys, please keep the discussion here and don't disrespect others that way. I'm like, if it just continues, I may have to ban someone if the comments, like offensive comments, right? You can talk about politics all you want, but don't insult each other this way. Like, not ban, right? Like, give a warning or something. Um, yeah. So we make the test. Yeah, we fail an assertion. It says that the memory ends up being corrupted in the end. So it's not even a problem with the way memory is arranged. It's a problem with whatever happens to memory. What? What even is happening? Dun dun. Out of touch and harmony. These silent blocks of Liquor Street. Chasing in. Oh, the problem isn't our testing. The problem isn't our testing. And I'll tell you why. It's because when we reallocate the block, we fail to consider the fact. Never mind. Never mind. I'm stupid. Didn't say anything. Please stop. Please stop doing this to me, Mr. Allocator. I think do you really need that assumption? Yeah. Because this thing is making sure that the data is still there. So it's just telling us like, oh dude, somewhere along the way you corrupted the data. Which is really bad. Unless yeah, no, like we're doing the right thing, brother. What do you mean? What do you mean? What do you mean? What do you mean? So we are in trouble because Learning Reform, saw your video on YouTube. Great work. Yo, thank you very much. Wait, I'm so surprised that there's so many people from YouTube. Um so wait, I didn't read your comment. Sorry. I want each my stream be scheduled. 0, 1 hour coding, 1 to 15 tech economy, 1 to 15, 130 impact of money on politics, role of tech, and then class work. Our orders roll in on this shot. How to act politically, 2 to 3 hours tech coding, kind of like that. Okay. Learn reformed. Hello. 808 was free before, is that right? You are so right. You are so right. What is happening? What is happening? Why are we okay? That is a pretty. It's pretty lucky that we see the free, like, in the exact same page as the realloc. Let's see what happens. Like, did we put something in there? Right? 808 is one of these blocks over here. It's this one. It's this block because it was previously allocated and then it's freed. And now we try to reallocate 24, which is fine. And then we try to reallocate 808. Yeah, something weird is happening. What? So it's a problem with our testing, not the malloc. Let's go. Thank you, dude. Vicente Alencar's on fire today. Yeah. So what this means is I cannot believe we were tracking it through the comments. The print heap thing was the best idea. So we have a malloc here, blah 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 blah. We freed the block. So we should be removing things from our Stevec. And indeed we do, right? Stevec remove. And then we remove them, but it seems like it's not working. I think the problem is the stable vector implementation. Like, I just did not test it and I just trusted that this was fine. So yeah, I don't know what to do. Because I don't want to test the stable index implementation. Wait. Why am I being stupid? Are there stable index vector in C? There you go. John Buffer. It's so funny. Oh, but this one's in C++, right? Yeah. Give me one that's in C. Please. 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 No. Okay. Anyways. I think we don't have one. So I think the problem is this implementation, right? Because like, for what reason would it be returning 808 if it is no longer inside of free? Right? Like, it shouldn't be giving me that back. I don't know, guys. I don't know. I don't want to check out knob. Wait, what do you mean by knob? You mean like knob vector? Like, is it? What do you mean by knob? Sorry. Wait. Yeah, I don't know. Zolzin's thing, knob.h. Ooh. Next iteration of the no build. Shorter and more suitable for a previous iteration of the idea. The idea is that you should not need anything but a C compiler to build the C project. Okay, it's like not suitable for a project. Okay, so how should I use it? How should I use it? Like, do we have? No. Okay, so the reason why we have a stable index vector is not because we need an array or something like that. Like, we need something that tells us which blocks we have. Okay, so we need to select a random block out of all the blocks we have allocated so far. But we need to select a random block that is currently allocated. Because if we select a free block, then we would be performing, say, a double free, or we would be reallocating a free block. So that's not right. So we need a container that stores what blocks are currently allocated. And that's the stable index vector. For a normal vector, no, because like, you know, removing an element from a vector is O of n, and that's like a completely messy. The stable index vector has just deletion of O of 1. Insertion O of 1, deletion O of 1, traversal O of n. So like that, it's just because of that. And like, since C doesn't have, you know, containers by default, if it had a vector container, I would just run vector.remove and not care about the performance. It's just like, you know, like here, I just want to live my life. I just want to do the fun stuff. I don't want to do the testing, bro. Okay. André, did he have some issue with build system? Oh, hi, Andrew. No, we didn't have any issues with the build system. We just have a problem with a data structure, a stable index vector. And the problem with that guy is that, he's a little special. There might be some problems with my implementation, and I don't know where the issue is. Let me search this. I don't know what it usually is. Okay. Fix Stevek. I know, but I don't even know if Stevek is the problem. Like, well, I kind of know, but like, then we have to create tests for Stevek, and like, bruh. Okay. So create Stevek, right? We allocate. Okay, follow me through the logic. When we create a Stevek, we allocate space for the IDs, we allocate space for the elements, and we could size. You're fuzzing it right now. Yeah, it turns out the entire testing process was to test Stevek and not the malloc implementation. And then we put indices in ascending order. That's good. When we insert, like these functions are just really simple. Like see how short they are, and they are still failing. Okay, when we insert, right, we want to make the last element to be equal to this guy, then we increase the size, and then we just return whatever ID we just got for him. When we remove, we grab the thing that we want to remove, we swap it with the thing, and here we swap it, and then we decrease size. So when we remove, we give an ID. We find what position that ID belongs to, right? And then for that position, or instead it's Stevek, use the red black tree. I don't want to use the red black tree. The red black tree is like even worse because the red black tree works with memory blocks. So we would have to make the numbers be accommodated just like memory blocks and have the same header and the same footer. No, no, let's not do that. So we have this guy, right? And then we get the position, right? We get the position of that ID. So now we know who it is. We store who that guy is. Then we say, okay, Stevek, right? Change the element. So swap the element on the last slot to here, and the same with the ID. Swap them together. And then make the last element equal to this. So this line is not necessary, although it doesn't change anything. The ID we do need to change with the position, right? Finally, we reduce the size of the Stevek, and then it stays the same. Perfect. Now, to get a Stevek, to get something from the Stevek, we simply compute the position from the ID, and then return that position in the elements. And to get a random ID, we simply say, well, select from here. Yeah, like select from all of the IDs. Oh, is this the thing? Wait. I think this is the issue. The Stevek random ID. This thing is what's failing. Yeah. Okay. So give me 1 second. So we need to provide a random ID, right? So we just need to return something that is within the confines of whatever we've done. Okay, I think rather than a random ID, I'm just gonna like say Stevek random element, random pop. Okay, so not gonna worry about that. I'm just gonna pop some random guy. He just has to go. Okay. So instead of BKID, don't care about that. Instead of Stevek get, don't care about that. I just want a random pop. Okay. So instead of Stevek, one random pop. And you're just going to leave this thing random from there. And I'm going to thank you so much after you do that. And that's it. We don't need to remove. We don't need to do. Never mind. Never mind. Okay. Take a look at this guy. Oh my God. Okay. So we need both random pop. The plot thickens. This is really bad. This is really bad because when we perform a random pop, right, we like pop this block. Okay. Let's just perform a random pop, right? And then we reinsert it. Brother. And then we reinsert it when we perform it. Oh my God. Okay. And then we reinsert BK pause. Yes, this is the way. This is the way. This is the way. Follow me, people. This is the way. I know the way. Okay. So what we're going to do now is we're going to say we need to pop a random element. So what we'll end up doing is we just pick something random. Position is going to be some random thing. So between whatever I have in size and the rest, I'll just pick, sorry, Stevek size, right? I'll just pick something and then I'll remove that something. And so what I'll do is I'll keep basically this exact same code, just copy and paste it here. De Ferrari, how did the allocator end up with vectors? De Ferrari, do not ask questions, brothers. Do not ask questions. Really bad things are happening in the bad allocators factory right now. What's going on is like, remember how yesterday we were doing the whole testing stuff? Well, guess what? It's still as insufferable as today. He is here. Yeah, the bird is here. Everyone say hello. So to explain it in more serious terms, we finished everything, and we finished like all of our malloc things, etc. Now we're trying to create some sort of fuzzer for the allocator, where we perform random operations and we check at every point in time that the state of the heap is something that makes sense. So we added a bunch of asserts to the original file. Like 1/6 of this file is just asserts. Assert. So after that, our approach was, okay, the asserts are going to be in charge of the checking. And what we're going to do is we're going to just create random operations like allocate, free, realloc, alloc, and the assertions are going to be in charge of checking whether or not everything is correct. The state of the heap is correct at every point in time. So what we do is first we pick some random operation. If it's an alloc, it's fine. But if it is a free and a realloc, we need to make sure that whatever we call that operation on is a block that's currently allocated. So we need some container to keep track of who is allocated. And that is the thing that I'm doing right now, right? We're creating this data structure, this stable index vector, so that we can keep track of which are the blocks that have been allocated. And it seems like there was a bug in the stable index allocator, not even in the stable index vector, not even in our implementation of things. So the testing file was wrong. And so now we are trying to solve that. And it's been like a huge journey. Like, it's so Anyways, we've been streaming for what? We've been streaming since 7:15 a.m. And then we took a 1 hour break. So you can like it's absolutely insane right now. Yeah. Ministero of Defense. Oh, Minister of Defense 79. Welcome to the chat. And yeah. Yeah, that's the reason why we're here working with these guys. And so I think this is it, right? I think this is it. Yes, I think this is it. I'm afraid you need tests for the vector. Rather, no. No, we are not testing the vector. I was so sorry. Okay. So I think we can just return temp element. And then I'm pretty sure it works. I'm pretty sure it works. TMP elem. TMP elem. And then elem. Perfect. Okay. All right. Once a name. You should follow TDD for this low-level stuff, right? The test first. Yes, yes. The thing is, like, we didn't even know what a test looked like yesterday. Like, it was so unclear what it meant to test the memory allocator that, like, it was basically impossible. Today we got a clear idea, and like we are like, okay, sure. And so now we know. I guess allocate some memory. All right, buddy. Zaner, welcome to the chat. And yeah, so right now we have the temp element. I think this is correct, right? If we want to pop some random element, just, you know, find some random position, grab that position, and then just delete it from the stable index vector, and everybody will be happy now. I think. Yeah. Yeah. Yeah, no. You know, put a little bit of faith on it and then it'll work. Make him test random. And then we do ./bins/mm test random. Moment of truth. No. Now it's failing even earlier. Bro, what? Wait, what? Now it's failing even earlier. Now it's failing on step 18. Previously it was failing on step 31. Okay, so the issue is different now, which is great. Let's see. That doesn't matter. You always write the smallest unit of failing test first. I mean, so how we did write very small tests at the beginning, right? Now we're trying to create like bigger tests. Because this is not like, oh, we haven't. No, we wrote the thing and we're gonna test it. No, we did create very small tests. Now we're creating this huge machine of tests, some sort of fuzzer that creates like a bunch of random data and stuff. So it is because of that we're doing this, and because why we are so trapped, right? Because now we're creating like a huge test machine, but we did create tests before, and in fact they are in test. There are these little tests, these like oh, alloc something, then realloc, and so on. So yeah. How would you test an allocator? Technical is something is in memory. That means it's free of side effects, right? Or I meant to write, if you're testing an allocator, would that mean it's free of side effects? Stephanie Saw said, hello. Beta testing is fun. No, it's not. You can get him on. Just look up TDD. Wait. Sorry. So wait, TDD is in test-driven development, right? Where you first create the test for whatever you are going to implement, create a small initial set of tests for what you're going to implement, and then you implement the thing knowing already what the tests are and simply waiting for that initial batch of tests to pass, right? So that you actually have a basis on when to on knowing whether your solution is right or wrong. But I might be wrong, so let me look up TDD. What is TDD in Python? TDD in software development. We write an automated test before you write the actual code. It follows a short cycle known as red green refactor, meaning you write a failing test, write code to pass it, and clean up the code. Yeah. Yeah, it's yeah. So over here, what we have, so we have a different issue, which is, I guess, great, because the previous issue made no sense. So yeah, make test random, we reset, and then we run it. / test random. Perfect. TDD comes from Uncle Bob. I would take it with a bit of a grain of salt. No, but I feel it is helpful. But yeah. Wait, let's see. Let's take a look at this. So what is going on and what is the issue? The issue is that it's telling us there is corruption of memory somewhere. Let's follow these steps. First, we malloc 157. Great. Then 102. We free the first one. We malloc 176. Yes. We malloc 132. So we split the first block. Perfect. We malloc 71. So we put it. Yes, we expand the heap and then we only reserve this section. We free 192, which allows us to free. Yeah, these two guys merge. Perfect. Then we reallocate 24. So whatever this guy is, we reallocate it to be of size 2023. So we merge these two together and then we partition them. Perfect. When we malloc 113, we need to find a spot. There is not such spot. So then we need to expand the heap. And when we expand the heap, we end up with a block of 120. We malloc 130, 192 is more than enough. So we split that block to accommodate for that request. Then we free block 24, which would be this guy, right? And then when we free that, it merges with the block to its side. And so we end up with this. When we realloc this huge block over here to be of size 181, we simply merge the two together. We merge this with this. Then we realloc the same block to be of size 226. And that should change things around, right? Ooh, what's going on? Ooh, do we have a problem here? I think we can improve our printer guy, because so let's improve our printing process, because we can simply go here and then where is it? Here, print heap. So I also want to print the identifiers, because notice that it just gives us the identifier, and it's, we can add up the numbers to know where exactly this is pointing at, right? I imagine 696 is pointing at like this guy, just because 272, 176, and so on. But it's better if we print the identifiers. So we just do the exact same thing. It's different from, and then there's gonna be a new line here. Is different from the no heap pointer. What we're going to do is we're going to say, well, please print the identifier of this guy. So that's going to be something like this. So 1, 2, 3, then the identifier, and then 1, 2, 3. Great. Okay, so we print the identifier. And then after that, we provide the actual identifier, which should be the current block. Yeah, I feel that works, right? And then we continue by saying that the current block is equal to the next block. Current block. Yay. Okay, I think that's enough. Let's wait. Hello. C extension, please load. Thank you. Okay, let's try and reset. Let's try and do make. And let's try and do an execution. Okay. Why am I not seeing the numbers? Oh, of course, because current block gets drafted by this guy. Yeah, sure. So we need to reset it. Perfect. So now we reset. And then we do this. And then the thing about, ooh. Hello? Oh, okay. Rerun it. Okay, perfect. Oh, shoot. Why is it doing that? Am I just doing 2 spaces? Oh, I'm doing 2 spaces. It should be 3. Then 1, 2, 3. Yeah. Why is it taking so much to compile? Interesting. Run this. Okay, that's better. That's better. So. Let's see what happens. Malloc 157, true. Malloc 102, free 24. So we're gonna free this guy, and indeed it gets freed. Malloc 176, Malloc 132. Great. We had that guy. We split these up. Malloc 71. So we're gonna allocate 71. We expand the heap, and we allocate a block of 72. We free 192. 192 is supposed to be this guy. This guy. And so now when he's freed, he merges with the one on the left and ends up being 168. Great. We realloc 24, this guy, to be of size 2023. Since there's something free to its left, they just merge. And they're a happy family now. Yeah, and the block gets split. Perfect. We malloc 113. 113 should say, oh, I don't have enough space. Let me expand the heap. And it does. Then it tries to allocate 130. 192 will suffice. And so it just, splits that block. Free 24. So 24 is this guy. And it should now be freed. And then it merges with the one on its right. Then we realloc 696, which is this thing. We reallocate to be of size 181, so then we just merge them together. And that's this. Then we reallocate 696. Why did this print twice? Oh, it's because realloc. Okay. We realloc 696 to be 226, right? And so 696, so this guy, to be a 226 wide block, there is no such thing, right? So we need to expand the heap, right? Like in this thing over here, do you see something that allows you to be 226? Oh yeah, never mind. This guy at the beginning. So then we transfer all of the information to 232, to block 24, sorry. And then we free this block over here. Yeah, that's the way it's supposed to go. Number 13, we malloc 128. So then we try and look for something, and it should fit over here, which indeed it does, right? So 128. And then we split the block because it's too big. Then we realloc 24 to be 35 wide. So 24, which is this block, which had 232, we shrink it to 35, and thus it becomes smaller. And then whatever's left merges with this guy. Perfect. Then we realloc 696, which is this that we are approaching the singularity. 696, we make it to be of size 2. 2 is too small. It can be at least size 16. And so, right, nothing really changes except for the fact that this thing gets split to be of size 16, and then the rest merges with 56. It's all fine. Then we malloc 127. Are there any spaces for 127? Yes, there is this one and there's this one, but this one is more appropriate. So then it allocates the 127 over here and it splits the block. Everything's perfect. Now we malloc 60 without looking. Where is 60 gonna go? Not here, not here. It has to go here, so it should split this block. Yes, it goes there and then it splits the block. The next operation, we reallocate 24 to an address of to something of size 145, which is possible, right? There's a 152 over here, and so we move all the data here. And then there's an assertion failure. The data has been corrupted. Also, I don't know if this interests you, but this is all virtual memory space. Yeah, of course, right? Malloc works in the virtual memory space, so yeah, like physical memory, we are not concerned about for that. We should use kmalloc, but yeah, no. Yeah, they're all in virtual memory, so I draw them together because they're still together in virtual memory space. But yeah, exactly. So what we're doing, some OS let you use a pseudo mode, have blocks next to each other. Oh, like in actual physical RAM. But okay, so Windows and Linux support it. I think in Linux you do it with a kmalloc, right? Because we were learning about that, like I think yesterday actually. Interesting. But there is okay, guys. We have a problem. We have a problem. Interesting. Windows supports it, which is kind of crazy considering how sometimes a little, underwhelming the Windows operating system can be. What is the problem here? What is the problem here, people? Why do we have this problem? Everything looks fine up until this point where we try to reallocate this block into something new. And so now we try to write the data here. So the assertion on line 49, the test random, only gets triggered when you do a realloc block, right? And so what it's saying is, after whatever happened to that block, things were not the same. So something happened there that just corrupted everything. I don't know what it is, but something I think we could do is just print what the data is. Well, we cannot really print that because for that we would need a because this is not a null terminated string, unfortunately. Since you can cache the others, yeah, I imagine. Whoa. Good. Okay, let's guys, let's think. Realloc block. We assert the memory comparison between the two. And then the memory pointer, right? What is the problem? Like there has to be something going on here. Either I'm not understanding or something is happening. What is the thing that bugs me out? The thing that bugs me out is, right, realloc always makes sure that at the beginning the data is there and at the end the data is there. Which means that the last call for realloc approved of the move and said, yes, the data is here. And so did the last call to malloc, right? To create block. So the only thing that can modify block information is realloc. Or allocating some other block, and maybe our memory allocator is just doing stuff that it shouldn't be doing. Let's do this. Let's run it, and through the debugger, inspect, after this assertion takes place, what each of these values is holding. right? I feel it's only fair. Let's wait. Okay, perfect. So we continue, we continue, we continue, we continue. We go to E3 test. We continue, we continue, we continue. We enter. Perfect. And then we let it run until it hits the assert. No, please don't stop. There you go. So now we take a look at the data. So the data is saying that it's just a bunch of ones. But according to main pointer is a bunch of f's. Have we reallocated 24? In step 14, we reallocated 24. Yeah. So actually, our data is the one that's wrong. And the reason why I'm saying that is rand bytes returns to you, right? It grabs the current seed and then it like generates a string that has just that specific number everywhere, plastered everywhere across the string. And then it increases this. Data is still holding 1, 1, 1, 1, 1, 1, 1, 1, 1, right? When it shouldn't. It should be holding something more updated. Because 1, 1, 1, 1, 1, 1 was the first time the block was created. In fact, this is the first block, 24. And so it's the, whenever it was created with seed 1. So the data 1 was what was plastered there. When it was realloced, the data changed to be whatever the ID was at the time. Currently, F or something like that should be the correct value, right? But it is not. So the problem is our test file. So there's something we're doing wrong in the test file. What is it? Data is equal to this, run bytes, and then we put the memory pointer, yes. When we realloc, what we do is this. We compare the data, right? We do all of that. Then we make the block pointer be realloc. Then we set the data to be the random bytes. Oh. No, never mind. What am I saying? Yeah, what? So we make the data become updated, right? Which is what this guy returns. And then we make the data size be equal to size. Then we copy the mem pointer and the data and everything. And that's it. Block data should not be concerned with anything else. Where are we using the block data? We're using it here. So let's see. The block data is here. Yeah, this is a fair usage. We ran bytes, we nalloc, and then we mem copy. Okay. Maybe we just do, we ran bytes, we nalloc, and then we copy. Is there a problem with that? There shouldn't be, right? So the order shouldn't matter. What if the compiler is doing some crazy optimization where it like sets the data size before the assert happens? That is not true, right? That's not true, but I'm just trying to find excuses. BK data and then BK data size. What is the problem? What is the problem? Same assertion. Okay. We run the debugger and we let it crash where it crashes. Why do we have that information not being there? Oh, well. Vini Gabriel 73, Jim says dead, Badid, Product Deviti, Jose Malucero 1984, Citronur, and Norskin. Thank you for following. Yo. Perfect. So we filled the assertion here, right? And so now we have this block that has a data size of 157, yes, as it should. But its data just points to outdated things. Why? 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 What is going on? Right? Look, let's see. What is hex 1005 FBD50 plus 24? It's whatever that is, but I want it to be displayed as hex. Okay, well, it seems like we cannot. Wait, or is it the memory pointer that is pointing at something that it shouldn't? I am so confused. I am so confused. I don't see why it's failing. Because then when we reallocate, yeah, what happens? What is going on? Why? Okay, let me take a look at the call stack. What are we doing? So here, the block that we end up picking in BK pause is block 0, right? Yes. So when we reallocate, right? When we reallocate, we not only reallocate that block to somewhere else, but do we ever perform a free on 24? Free 24? We do. We do. So why is block 0 being brought back? Okay, this is another problem with the Stevek. Oh no. Oh no. Yeah, what's the problem now? Dude, we're doing things right, no? Like, what is the problem? The Stevek. I hate you, Stevek. Oh, it's the +1 again. Oh my god, dude. So okay. The bug is this. When you want to generate a position, you want to generate a position inside your vector, right? So what are the possible values? The values are from 0 to the amount of, the amount of elements you have minus 1, right? So if your vector is 3 elements long, the sort of space from which you're drawing is 0, 1, or 2. If I add a +1, it means that this thing is going to behave as modulo 4 in the example of 3 elements. And modulo 4 allows for 3 to happen. And so what's happening now is that 3 is a possible value despite 3 not being an element in your vector. So this plus 1 doesn't go there. No words. No words for what just happened. Now we have a seg fault. Where is... Huh? Where is the seg fault taking place? Oh my god. Okay. This is not good. This is not good. No good, no good. It's not good. Okay. Let's try and see where it happened. So if we run the debugger, I refuse to leave until we have solved this. Like, well, no, it's not that I refuse. I need to talk to other people too, but... Let it run. Bad access on some random header in some random function, which we don't even know where it comes from. So let's see. Here, we're trying to do a remove. So we're trying to access some sort of data. Oh, so we're trying to remove something like that doesn't even exist. What? Okay. If p block is different from null pointer, remove p block from the red black tree. So who is p block? 536. 536 is this guy, right? So we're trying to free 808. So when we free 808, which is this guy, we want to take a look at what things can this guy merge with. It can merge with the thing on the right. And it can also mean segfault means you don't assert enough. Yeah, I guess so. And then it also means we'll see. Maybe the error doesn't have to do with a bunch of stuff. We'll see. So and then we look at the left and we see, oh, once this thing is freed, we want to merge with the left. So this is correct, right? We grab the p block, we see that it's 536, and then we remove it, right? We remove it from the red-black tree, 536. The thing is, the red-black tree is telling us, no, brother, right? That this thing doesn't exist, or something like that. I don't know what the red-black tree is saying. I don't talk to trees. Plug this in, perfect. So what's going on is we enter this, let me check something. Okay. We enter this function, this red-black tree remove, and then we go through the process. Like, do you have a successor in the red-black tree? No. And in fact, it shouldn't. The blocks that are free are 16, 40, 264, and 152. 264 is, if anything, the biggest block. So it must be at the leaves. And because of that, it doesn't have children. Since it doesn't have children, it doesn't have a successor nor a predecessor, and it doesn't have an heir. Now, we notice that it's not the only node left, and we notice that it doesn't have an heir. We know that it's a DB nil, so that's true. And then we say, well, if the color of this node is red, then try and link the two together. So the problem is here, where we try and link them. Something is going on when we try to link them. So let's see what happens. When we try to link them, we say, well, do you want to link... Let me go back, well. What I want to say is, if it's red, just delete it. And the way you delete it is you find the parent of the block, and then you replace the current node with a null pointer to say like, oh, you don't have a child anymore. So when we go to t-link, right, we say, well, this would be a right child. So now what we're going to do is, well, if the right side of the parent is not a null pointer, which in fact the to-be parent is 192, so ooh, we have a problem. And the problem goes deep. It's a really bad problem. Because notice this. When we, oh my God. So if I get BK parent of the current block, oh no. Okay. So the current block is 536, right? Which is this guy, right? And so if this is the red black tree, it should have as parent a node that is in the red black tree. But you take a look at 192, 192 is allocated. Yet it's the parent of this guy for some unknown reason. So what is going on? Where do we mess up this bad? When does the parent of this thing suddenly become 192? And why is it happening? So the parent shouldn't be this thing. Let's check something. Yes, set is free to true. So then after we do this, we call as the blocks. We make the block. We set the block to be, yeah. Then we insert it in the red block tree. Yeah, this seems to be completely fine, right? So the error is coming from somewhere else. Like it's coming up the chain. And it's really bad. Oh no. Okay. So how can we detect where the issue is happening? We yeah, that's it. We what? We what, brother? We what? CT Flux, thank you very much for following the adventures of a dying man with a something so irritating as this. Where is the mistake? So we try and find this thing, right? We say arbitrary insert, arbitrary block. Yes. Coalesce, right? The order matters. Do not use the previous block unless you know that the previous block is free. Sure. Hello, Just Robbie. Hi. We're currently in a very bad situation. Polyglot, welcome back. Welcome back. We're in a really bad situation. Are you trying to allocate a No, we're not trying to allocate a red-black tree. We're using a red-black tree to keep track of the memory blocks, right? Right. And right now we are suffering because there is a seg fault somewhere. We know where the seg fault occurs, but the cause for the seg fault happens way before. We don't know at what point in time the thing that allows the seg fault to occur gets introduced. I guess one thing we can do, and you guys are gonna hate me for this, I am sorry. I'm really sorry. I apologize in advance. Since we have a problem with the parent, I want to make sure that we can print who the parents of each block are. Right? So after printing this guy, we can print again. Is red-black commonly used to track allocators? I don't know. So what we did is we started from scratch. We didn't look at any implementations, right? And we designed our allocator from scratch, like literally from scratch. Just, going like, okay, what would be a good thing to use? And we used the red light tree. So there you go. It's just because of that. And it's not a dumb question at all. Like, it is the fundamental data structure of a mem allocator. So if anything, you should question it. Yeah. So let's see. So maybe here we can print, instead of that, we can print the parent. So, right. So if the current block is free, then we want to print the actual parent, so bk parent of the current block. Otherwise, we want to print 0. Right? Right? Okay, yeah. And so everything should be fine, right? It's just a balance tree by marking some nodes red and some nodes black to figure out balancing. Yeah. Yeah, a binary tree, a binary search tree. A red-black tree is just that. It's like a binary search tree with steroids that make it more balanced and the search a little, better. But yeah. So I think we can just print who the parent is. Oh, sorry, I modified it in the line it shouldn't be modified. Sorry about that. There you go. I should have done it here. Ctrl V. Perfect. Okay, let's reset. Let's apply the think of this guy like a child, right? It's like, you need to, despite maybe, if you have a little son, your son may be very annoying, but you have to treat him with patience and care and love, because only that way can you raise a good person. So we're doing the same here, right? We are connecting with our internal self, and we're projecting it into the debugger, which is now going to provide us all of the information we need, because the debugger is, if it was a human, it would be a great person. And that's what we're seeing right now. Oh, shoot. Okay. And that's what we're seeing right now. Thank you, debugger. Everybody say thank you to the debugger. Never mind. This thing is stupid. What is it doing? Why is it printing it that way? Hello? Why is it printing in separate lines? Bro, under what? Okay, no. I think we're good. So, it has no parent. It has no parent. This has no parent. And this is the root. So it has parent 0. There's the root. Everyone's here, so this is fine. Yeah, line warping. I figured at the end, yeah, because I saw the other ones were okay. Now, this guy becomes the root, so everyone, nobody has a parent. This is the root. And then, okay, yes, your parent should be 168. Okay, perfect. See, the numbers are not aligned. Does anybody have a good idea on how to actually align the numbers? Because it's also driving me insane. I think it's okay. We can just keep track of them. So yeah, 168 is your parent, which is indeed a free number, right? 568 is indeed a thing, right? Then 568 is indeed a free log. So yeah, no extraneous parents. 800 is indeed a thing. 800 is indeed a thing. We're fine. this is the root for some reason. That's fine. 24 is indeed a thing, and 24 is indeed a thing. Here. 800 is indeed a thing. 800 is indeed a thing. And 0 is indeed a thing. So we're fine. And here. 448 is a valid parent. 0 is valid. 0, 0, 0, 0, 0. 448 is a valid parent, yes. Then we free again. 448 is a valid parent. Yes. 488 is not, but 448 is. Then here, 0. 448 is a valid parent, and 448 is a valid parent. Yes. Okay. 760 is a valid parent, because it's free, and 760 is a valid parent. Then 0 is a valid parent, yeah. 808 is a valid parent, yes. 808 is a valid parent, yes. 448 is a valid parent, 448 is a valid parent. 448 is a valid parent, yes. 160 is a valid parent, and 448 is a valid parent. 808 is a valid parent, right? 448 is a valid parent. 448 is a valid parent. So we just take a look at whatever they're pointing at. So these are the identifiers. So if I say 448, I travel to 448 in the first row, and then see if it's free. If it has a line, it's allocated. If it doesn't, it's free. Let's see. 448 is indeed a valid parent. 0, 0, 0. 448 is a valid parent for you. 0 is a valid parent for you. Yeah. This is where the problem happens, allegedly. Let's see. Here. 448 is a valid parent. Let's see. 0, 0, 0, 0, 0. 448, yes, it's a valid parent for you. Then 0, 0, 0. 448 is indeed a parent, is a valid parent. Okay. Okay. So wait, polyglot, it's not really a space. Like we don't need to just add a space. Like these numbers are like multiple digits long. We don't know how many digits they have. So we need like a little bit of a more sophisticated function, but like I just want to get this thing done. So I'm just gonna do it like this. When we reallocate, yes, 448 is free, so it's valid. Yeah. Then here, 1056. Is it a valid parent? Yes, it's valid. Then 448 is a valid parent, and then same as this. Wait, previously we failed on step 18. So what happened? What? Did we just not fail? Oh, sorry, no, we failed on step 28. Yeah, so it seems like, okay, this one is not a valid parent because 192 is occupied. Not a valid parent still. Still not a valid parent. And then here, 192, yeah, not a valid parent. You shouldn't be doing that. 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 You should be doing that. Okay, so we free, okay, this is the root of the problem. We free block 568 for some reason. So when we free block 568, our rotation is triggered. Whoa. Whoa, what do you mean? Whoa, this free should not be allowed to happen. No, never mind. It should. Sorry. We free this and then it merges with this, and that's 536. And so when that free occurs, This guy, so 448 inherits 192 as a parent. Then we reallocate 304, which is this guy, to be 227. So then it merges with the guy on its left. And when it merges with the guy on its left, this guy still preserves. Well, it isn't even that guy, right? Who is it? Who is it? Tell me right now. We reallocate 304, 227. So 304, which is this block, we reallocate to do 227, which should be more than enough with only merging with the left. So you should merge with the left, which indeed is what happens, and then 32. Yeah, then everything goes back to normal. But now the 192 changes to be... So do we just fail to remove from the red-black tree at that point in time? Let me go to reallocate. Okay, give me 1 second. So we'll be back. Let's see what it is. Don't control yourself. Don't think on me what you need from it. Okay, so what we have here is this 192, right? Is the parent of this guy. 192. And so now what happens is when we perform that reallocate, we reallocate block 304, which is this guy, to be 227, so that it needs to merge with its left. And when it merges with its left, our removal should be triggered. And I think that's what happens. It's just that something weird happens here, right? So let's see what happens with reallocate. With reallocate, we go to this place, right? Over here, we assert that this is valid. We merge the two together. We remove it from the red-black tree. And then we coalesce the two blocks and set this to not be free. So in the moment we remove from the red-black tree, that 192 should be gone. But it isn't. So it is a bug in the red-black tree, which is incredible because allegedly we had tested the red-black tree. So, you know, Edu007YC6Z, thank you for following it. Same for Team Luca and Lezardav. Yo. So, we have an issue. We have an issue right now. We have an issue. We have a problem, to say the least. The situation. And that situation is not pretty. No reason why it should be pretty, but, you know, it is what it is. So, Okay, okay, okay. I'm gonna propose something really extreme. Please don't burn me at the stake. Okay. Uh, you're acting like a because it is. Okay, yeah. It's just that I'm it's like I've been here for what, 9 hours? Yeah, 9 hours basically. And so it starts to take like a mental toll on you. Like your sanity is like slowly but surely descending. And so tell it bad program. Yeah, bad program. Bro, behave better, bro. Please, bro. Okay. So yeah, what we're gonna do is we're gonna say, um, you guys may kill me. Once again, don't burn me at the stake for this, but we should also print the color, and then we should just perform whatever operation is going on here to see if the red black tree is just doing the incorrect thing. Right? So I have gone insane since I worked with virtual memory, dude. My respects, because this is like absolutely insane. So yeah, your debugging methods are too extreme for me to no. I don't think so. I think they're just stupid. They're just stupid. Ah! Okay. So the error happens here, right? Like you do the realloc, we remove this thing from the tree, we remove 192 from the tree, and for some reason it stays there. So the tree fails to update somebody. Can you find a minimal seed where you failed earlier? Like, it's not even, I feel that's not even the problem, right? The problem is like, we already know where the issue is. Like, we just have a completely valid heap like this one. And when we perform the removal of this node, bam, right? We fail. And so I think, like, because we know the state of the red black tree at this point, if we just perform whatever the removal needs to be, we would be able to know what the problem is. Right? So I think we can just draw it out. I think we can genuinely just, draw the red black tree. And so here, so we're gonna involve the parent in parentheses. We'll put the next %d, and then make it be the color of the block, pk color, and then block, or cur block, I suppose. Invalid conversion specifier, brother, please understand. My family and my children depend on this working. Please understand. Program. Anyways, we run this. We run this again. Let's visit the weird state. So the weird state is on line 20. Add /t instead of this if you're using it instead of the 4 spaces. I'm not using 4 spaces. I'm using like 3. Like it will align it up. Really? Oh my god! Is that the thing? Wait, that's crazy. Wait. -t and then -t. So something like that, right? Right. And maybe I do -t. And then maybe I mark allocated like this, and -t. So it's /t. Then I do /t. Okay, hopefully it works. If not, we just change it back. It's fine. /t min /t. If it does align it, that'd be wonderful. Because right now, it's very, you know. Somebody fire Polyglot. You're getting banned, Polyglot, bro. Wait, no, it does align them. It's just that, like, it's really dang. Yeah, no, it does align them. You're right. It's just that it's too wide, right? And so it doesn't really fit in the console. Like, yeah, it doesn't really fit in the console. But in these ones, it's pretty good. Hold up, you can set size. Really? Wait, how? How can we set the size? That'd be great. Say Geronimo. Say Geronimo. Say Geronimo. Let me delete maybe the first ones, and maybe that way we save space, and then it ends up printed pretty well. Oh. Yeah, this works. Okay. This is enough. Kind of. Question mark? No, I don't think it aligns. Okay. It's fine. It's fine, guys. It's fine. Don't worry. Don't worry about it. We're gonna have this. Oh, sorry. I for some reason deleted that, which I shouldn't have. Okay. Reset. Make random. That feels somehow worse. I think, yeah. Let's follow your approach of setting the tab width. Okay, so what did you send me? You sent me this. Tab character width in the terminal. Where's the dollar? To set the tab to 2 spaces, use this command in the terminal app. -2. Replace 2 with your desired width spaces. Ooh, okay. Let's do that. Tabs and then 2. Tabs in this and then 2. Reset. Tabs -2. Make. No, it still prints at 4. It's fine. We'll just, you know, we'll adapt to it. We'll adapt to it. Yeah, but it'll look weird. The tab just aligns it to the next 6 spaces, but I guess you learned something new. Yeah. So, see, I feel this one is just good enough, right? Yeah, I think I found it. Okay. Perfect. This seems good enough. Yeah, okay, perfect. They're aligned. So line 20, or like operation 20, was the one where we were failing. 19, 20 here. Where we had 192 as a parent, despite the thing being allocated. So let's take a look at 19. Guys, I am so sorry, but time to get our artistic skills because we're drawing this red light tree. Okay, everybody prepare mentally. So we start. Make this thin. Okay? Make this thin. And then let's do 24 is allocated, so it doesn't belong. 192 is there, and it's the root, and it's black. So 192 is part of the tree, and it's black. Okay, black is 1. C Films, hello. I'm doing well. How about you, C Films? Well, I'm not doing well. We're debugging this. We've been here for 9 hours, and you know, yeah, it's starting. I'm so sorry, C Films. I didn't see your previous message. I was very, very concerned with this. Yeah. Okay. We're working on a memory allocator, as the title says, and so currently we're trying to solve a bug with our memory allocator. And it's related to a red-black tree that somehow it's failing. I am not sure why. So we have 32. So we have 104. You are going insane, bro. Yeah, I know. You don't have to tell me. You don't have to tell me. Yeah, I am going insane. The more time passes by, it like becomes, terrifying. Anyways, we have 32 as a child, and it's black. And it's the left child since it's smaller. So 32 is here, and it's black. Great. 32 is there. He's really happy with life. Then this guy, 264, has 1056 as a parent. So first we insert 1056. The fuck? Sorry. Do you guys see this? We don't want memory for something specific. We're making a memory allocator, which is the one that is in charge of providing a programmer with memory. Or not memory, but like, the one that manages a programmer's memory. When you call malloc, when you call free, that is the guys that goes there. Prices are insane. Yeah. Oh wait, you meant that sarcastically, right? What do you want memory for? Probably. I don't know. Sorry. Okay. Guys, do you see the problem? Says the mentally ill man while there's a wall of numbers. Yeah, bro. Yeah, okay, so 192. So 192 is free, right? And so it is the root because it has no parent, and it's black because this is 1. This guy, 448, is also... What am I talking about? Dude, no. I should be including the sizes. Okay, so here, 104 is the root. Because the value of the element is the size, not its identifier. 104, which in parentheses we write it's 192. Right, 192. It's block number 192, and its size is 104. Right, so this guy over here. It has no parent, so it's the root. Then we put this guy, which is 32. 32 is a child of that block, so 32 would go to the left, right? 32 would go to the left. And it's also black. It says over here. It's a parent of 192, and it's also black. And 32 is identified by 448. Then we go here, and we see that this guy, block 536 with size 264, has 1056 as its parent, so not yet. Let's come back to him. 152, right, so 152 is the right child of 192, and it's also black. So 152, 1, 5, 2, right, 152, which is, its identifier is 1056, is the child of that guy, and it's also black. And finally, this guy, 264, is the right child of 1056, and it's red. So the tree looks like this, right? the tree looks like this. The tree looks like this. 264. 264. Oh wait, I think the camera is covering a part of this. There you go. 264, whose identifier is 264, whose identifier is 536. Okay. Wait. I know it's weird, but I would personally understand more if it was in hex and with padded zeros. That proves I've gone insane. Bro, no. You're on insaneness level 2. You do not want to see my notebook. I don't understand the thing you're saying. I just see a tree. Yeah. Okay. You should see the tree, right? That's all we care about, honestly. But fair, talking out loud is a great debugging method. Yeah. So what we see over here, just think of this tree, right? Of this tree. What we do is we reallocate 304, right? So look for block 304 is this guy here, as you see me pointing with my mouse, 304. This guy, we're going to reallocate it to something that is 227 bytes long. So what we're going to do is we're going to merge it with its left, which indeed is what happens in the future. But we merge it with its left. Okay, we merge it with its left. And when we merge it with its left, yeah, there's a realloc. Brother, what do you mean? You know? Yeah, there's malloc, free, and realloc. It's the Holy Trinity. Is the trio then. So realloc is the one that's causing the issues. So we created it like 2 days ago, if I remember correctly. Yeah, me too. But like, you know, we need to implement realloc too. So we have 136, especially because vectors make use of realloc. Okay, 136, right? 136 merges with the one on its left. This guy. What that means is that this guy is going to stop being free. It's no longer going to be free. So this tree changes. This tree changes because we need to eliminate the root of the tree. So what is it that happens? What happens is we take a look at 104, right? Okay. We take a look at 104. And then to delete things from the tree. How do we proceed? Well, according to what we know, right, we find an heir, privileging the successor. So we find the successor, right, of 104, which should be 150. This guy should be this guy. And then we switch them together, right? Yeah, we swap them. And then we set the colors to be exactly the same thing they have been. So let me make sure we have a copy. Yes. So this thing stops being, so we swap them basically, right? We grab this guy, and then we move them, and then we swap him here, right? Aha. Aha. Is this the problem? Yes, this is the problem. No, is it the problem? Wait, what? That question mark is very infravalid because it should be more valid because I don't think this is the eureka moment. How do we delete the root of a red black tree? I forgot. Oh my god. So we proceed with normal. I think this might be the issue. Oh no. Oh no. Okay. I see. See the problem. What happens if we go to the red black tree visualizer and then I do something like this? We recreate this thing. Oh, shoot, what? Shoot. This is not what I wanted. Okay, that's fine. Let's bring it to this workspace. And so what we want to do is to end up with a red black tree like this. So then maybe we insert, let's see what happens if we insert them in order. Insert 32, then we insert 104, and then we insert 152, so then it should rotate. Yes. And then we insert 264. And then it becomes the thing we have. Yes. Well, black, and red. This is a valid red black tree. And so now we need to see what happens if I want to delete 104. Right? So 104, what does it do? Delete. It goes here, it goes to 32, and then it replaces 32. It looks at the null leaf, and then it goes, okay. Oh, shoot. So it means that we need to travel. Can we ever have a situation? Yeah, I think, okay. Trust me. University of San Francisco, okay. Let's do this one. 32 insert. Hello? Brother, where are you? Oh, that's so small. What the hell? Why is it so small? Okay, 32, 104, 152, then the tree rotates, and then 264. Perfect. If I insert 24 or 20, it should be fine. Yes. And so now the question is, what happens when I delete 104? Right? So I'm gonna decrease the animation speed to be this much. So deleting 104. We pause. Okay, we step forward. We replace it with 32. Yeah, we replace it with the successor, right? We bring this here, and then we rotate. Oh no, we color it black. What? So the state of the red-black tree after this should just be exactly that. No. It should be grab 152, put it in your place, No, sorry, 192, put it in your place. And then, right, push 264 up. And then color it red, color it black. Right, so after we perform the realloc, right, yeah, there's something wrong with our red-black tree. Because what do? So in the scenario of this tree, we try to remove the block, which is 104. We try to find a successor, a predecessor. The successor is 152, right? And so with 152, we exchange things, and our colors stay the same, right? And now this thing assumes that we've ended up being replaced by a leaf, which is not the case. This is not a leaf, people. This is not a leaf. Is this mystery solved? Yeah, this is not a leaf. So this very specific situation is not a leaf. So why is that? So what do we do instead? This was not in the rules of the red-black tree deletion. Like, what? Let me add that test to the red-black tree things so that then we can test it. Bool. Test from hell. It's really simple, actually. It's really simple to do it. We simply need to create a red-black tree, create a bunch of blocks, and then start doing whatever we want with it. Okay. So we create a red-black tree, and we mimic the same situation. Where we do... Sorry, not this. I want the Excalibur. Where is the Excalibur? Where we do 104, right? So instead of 104, I'm just gonna have them be like, you know, like 10. Oh, well, not 10, right? Maybe like 1. Then it's like 100. I think this S already does the align work. Oh, okay. 10, 1, 2. Well, P104, right? P32. P32. P104, which does exactly this. So this 32. 32. 104 does that. So we do 152 here. And then we replicate again. And we change this to be 264. Okay. Okay. And so now we do the insertion. So arbitrary insert into our red-black tree. We insert P32. P32. And so what we should expect should be something like this, right? Assert that the red-black tree looks like a single node in which we have the root be black and its value be 32. Perfect. Now we insert into the red-black tree P104. Right, so red-black tree and then P104. Great. So now we assert that the red-black tree is equivalent to this vector over here. Then we say, well, put into my red-black tree this node, there's 2 nodes now, and they're gonna be split, and they're gonna be saying, yeah, CS node this, a black 32, S32, and then a CS node red S104. That's perfect. Great. Hello? What's going on? Expected a comma. Oh yeah, of course. Comma. Two few arguments to function called brother. What are you talking about? That's exactly what you need. Oh no, no. No, 1, no, 2. Okay. So now we do the same thing, but again. We do it again. Because now we need to insert P152. P152. So P152 changes things around because it makes the root become 104, the left be a red 32, and the right be a red 152. Perfect. And then we test the last insertion, where it should be something like this. Red black tree 104. We insert P264. So the tree should look like the thing we have on our right. It should look like the root is a black 104, the left is a black 32, the right is a black 152, and the right of that is an S264. And it's not two, it's four of them. And same for you. And the same goes for you, which you're 3, and you're 3. Okay. Okay, I guess the test goes a little further because then we can insert 20, P20, right? And then assert that the red black tree equivalent vector is this thing, node 5 actually. And then this guy here with an comma 5, then CS node. So all of these guys, the exact same. It's just that after the root, after 32, we have another red. We have a red S24. Not P20, but P24. And in fact, this guy needs to be red. 264. I saw a message in chat. Give me a second. 264. Perfect. This is it. People. This is the test. The holy grail of tests. If we pass this test, we have achieved eternal life and whatever. Let me create T pointer T for T24 of a line size of 24. Bald Samuel. Bro, where do you live? How is it not dark yet? Okay. Are you Brazilian? Because of the KKK? But I live in... Yes, you are. Okay. I'm currently in San Francisco in the United States. So, yeah, it's still pretty bright. It's 6 p.m. Oh, wait, what? The creator of Velcro died? No. Wait, that's pretty sad. Wait. Brother, what are you talking about? Dude, he died in 1990. What are you talking about? Bruh. What do you mean, bro? I believed you. What? It's a joke. Dude, wow. What do you mean? Read the whole thing. Wait, the man who created Velcro died. The man who created Velcro passed away. R.I.P. LMAO, bro, it's a joke. Read the whole thing. What does it mean? Wait, I'm so confused. I'm so confused. Like, R.I.P. Like, RIP. Oh, like if you were separating two things with Velcro? Is it that? Is it that what you're referring to? Like, RIP? Yes? Okay. Slash timeout. A polyglot. Bro, no. I'm not gonna time you out, but dude. Mm-mm. Anyways. Okay, this is the test. This is the test to govern them all. And then when we do arbitrary remove, we remove from the red black tree the root, P104. And all hell is called loose. Because now we need to assert that the tree looks a certain way. It should look like arbitrary equals vector of a red black tree. Looks like 4 nodes instead of 5. And then we do CS node. It should have. So what was the final state? I think we have it on the left. Yeah, it was this, but this guy converted to black. Or something like that, right? What was it? Everyone black or everyone colored red? I think it was black, yeah. You transition to black. 264. That is the final state we want. But in the case of and then some red 24. Okay. So it's gonna be this. It's gonna be a black S152, then a black 32, then a red 24, then a black 264. These should not be like that. These should be comas. And then black. Okay, there you go. And then this guy should be a 4. Reset. And then let's, oh my god, make arbitrary test. But first we need to call test from hell over here. Somebody put me out of this misery, please. Arbitrary test. Yeah, we failed that thing. It's not equal to that. So, did you ever have a kick that was terrible king Gary roller? I actually had never heard that joke before. It's kind of clever. So now we're gonna stop right here. And we're gonna check what it does. So my thing is, I guess there is a more fundamental problem. When presented with this situation of a red black tree, I don't know what to do. Right? If you, oh, what the hell? Okay, there you go. Oh, if you insert 10, it's gonna insert it always to the left, right? Wait, what animation speed? Brother, what are you doing? Oh, okay. It's gonna insert it always to the left. So it's gonna do step forward, it's gonna see this, it's gonna prepare the two, and it's gonna attach it, and that's it. Right? Perfect. And so the problem comes when it comes to removing the root, right? What happens here? So we change ourselves with our predecessor, right? So let me take a look at this, but in the code. So, right. So it's something very similar, only if we had a 20 over here. Right? So if I grab this entire tree, I copy it, and then I put it over here. Oh my god, the stream must be so boring for you guys. I am so sorry. It's just that we need to discover this issue, and I really don't want to go without solving the issue. I'm so sorry if it's boring. But it must be done. It must be done, unfortunately. So the problem here is this, right? When you ask remove the root, what are the things that you should do? So currently what the red black tree file does is it goes here, arbitrary remove, right? It removes the element as if in a BST. And so it finds the successor, and the successor is 152. So it grabs 152, right? And then it swaps them both. So it swaps 152 to be here and 104 to be here. Perfect. And then it marks 104 as a double black, which I guess I'll do with lines. Don't go there because you'll never return. Okay, with lines, right? 104 is a double black. So then we say, okay, block is now thought of as the double block node. Is it red? No. Is it the root of the red black tree? No. Is its sibling black, both of its children's black? No. Is the sibling red? No. Is the far nephew, is the sibling black? The far nephew black and the near nephew red? No. So we go to case 6, which is the far nephew is red, the one closest to you is black. And so what we do is we say, well, right, grab the color of the parent and then set the color of the parent of my block, which would be 150, 152. Happy Tofu Day? Oh, great. So TMP, right, color of my parent. Set the color of my parent to be the color of my sibling, which is black. Right? Great. The color of my parent to be the color of my sibling. They stay the same. Set the color of my sibling to be the color of my parent. So they stay the same. If I am a left child, which is not the case, but if I am a right child, which is indeed the case, we right rotate the tree at the parent. So we do something like this. We right rotate the tree, and we grab this thing, and this entire thing, and then we paste it here. Right? Then we rotate in the direction of myself. And so when we rotate, we end up with a tree that looks like this. Right? So it's like you're now the new root. 32 is now the new root. When we rotate, because we right rotated. And then we simply say, yeah, if it's nil, then do that. Then set the color of the far nephew to black. What? What? Okay, I think we're gonna need to go back to the article. Arbitrary deletion. We need to go back to that article that taught us how to delete things from the red black tree. Just absolutely insane. Like, this is a blast from the past. Let's see. Swati, please help us. Let's see. Why I need a red black tree? That's fine. We have a nil node. Yes. Every leaf node has a unique invisible child, yeah. Equivalent. Deletion cases. A red black tree should still remain a red black tree after an element key is deleted, yeah. Okay, so these are the problems, but let me see something. So it says, yeah, so it just says like, oh, right, come back to this table whenever you need. There's this, okay, example, deleting 30, but 30 is not the root. Like with 30, yes, we understand the problem. So we first have to search for 20. Once found, perform BST deletion, assuming you know it. Find either the maximum of the left subtree or the minimum of the right subtree and replace 30 with that value, which is exactly what we're doing, right? This is BST deletion in short, right? The resulting red black tree will be like 1 in figure 4. Element 30 is deleted and the value is successfully replaced by 38. Another task is to delete the duplicate element 38. Yeah. Go to the table above and you'll observe that case 1 is satisfied with this tree. Yeah, so we have to follow case 6 because of what we saw, right? We swap the color of the perform a rotation of parents in the direction of me, remove the double black sign, and make the node normal black node, which cannot be the case. Then change the color of the double black sibling's far red child to black. No, this is not the way it works, because like, if node to be deleted, so let us take a look at our example, and like, are we just imagining things? Like, is this just not real? What is going on? Because if we take this drawing, right, to the full screen, we take it to the workspace 3, you'll see here that it says, okay, right? And suppose then that here on the left, there is a red 24. A red 24. Brother, a red 24. Hello? A red 24. There you go. So we're going to have a big problem, because if the node to be deleted, so we want to delete this node, right? So let's follow the article exactly, right? To the T. It says, first perform BST deletion, right? Where does it say it? Here, so for a node, you first have to search for 30. We already know where 104 is. Once found, perform BST deletion, okay? Basically, right, find either the maximum of the left subtree or a minimum of the right subtree and replace 30 with that value. So that's exactly what we'll do. We'll find the minimum in the right subtree, which is 152, and then replace it with that value. So we copy 152, and then we put it over here, right? So we grab this, then we put it here. Replace it with that value. The resulting red-black tree will be looking like figure 4. Element 30 is deleted and the value is successfully replaced by 38. So in our case, the value is deleted and it's replaced by 152. But now the task is to delete the duplicate element 38. Go to the table above and you'll observe that case 1 is satisfied by this tree. So notice that now, right, now that we have this, who is the double black? The double black is the guy that we want to remove. So we want to remove this. Right, that's the double black, not the double red. The double black is this guy. Hello? Is this guy. There you go, right? And so now we go back to the table and it says, case 6 is the one that applies to us, right? Double black sibling is black, and double black's sibling's far child is red. This applies to us. So then we swap the color of the double black's parent with the double black's sibling color. Both are black, so it's fine. Perform a rotation at the double black's parent in the direction of the double black. So we perform the rotation. That rotation will end up giving us this. Right. This guy. We rotate to the right. We remove the double black sign and make the node a normal black node. So it's not that we delete it, we just make it normal. Change the color of the double black sibling's far red child to black. Change this thing to be black. This is invalid. This is an invalid red-black tree. Delete 15. So 15 is a root node, so it has no problems. Delete 15 from this figure. It's a root node. It has, sorry, it's a leaf node. It has no problems. Oh, here he's deleting the root. Oh wait, no, but like it has leaves that are immediate predecessors, so then it shouldn't be a problem. Oh my god. Okay. Yeah. Delete 15 from figure 3. It's still a leaf node, so there are no problems. Wait, okay. Am I just stupid and I don't know how to delete the root of a binary search tree? Did I just forget how to do it? That might as well be the case, no? Wait, where is Firefox? Here, okay. 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 Wait. Where is the other window? Oh, I opened it as a private window. Oh wait, no, I didn't. Wait, where is the other window with the Medium article? There is no such thing, it seems. Okay, that's fine. What was I gonna do? How to delete? I cannot believe I'm looking at this. The root of a binary search tree. Are we just being? Am I just being dumb? So I don't like geeks for geeks. Yeah, there you go. Deleting root node of a binary search tree. Stack Overflow. Oh, never mind. Okay. Maybe we can visit Geeks for Geeks, although Geeks for Geeks is a RAM consumer. Given the root of a binary search tree and an integer x, delete the node with value x from the BS tree. Yes, but we want to see what happens when you delete the root. Node has no children. That's fine. Node has one child. If the target node has one child, we remove the node and connect its parent directly to its only child. This way the tree remains valid after deletion of the target node. Okay. Let me think. I mean, sure. Right? So we only have one child. We replace it with, let me think. Replace things with our child. And then we remove ourselves from there. So then who inherits the double black? Anyways, what happens if you have two children? To maintain the BST property, we find the replacement node for the target. Do you notice? Yes, once the replacement node is chosen, we replace the target node's value with that node's value, and then delete the replacement node, which will now fall on the case 1 or case 2. Oh my god, wait, it's so slow. What happened to this website? Dude, please leave me alone. Yeah, delete two children means replace the node with its in order successor or predecessor and delete that node. And that's exactly what the guide is not telling me to do. Like, what is going on? So here, I want to pause the animation. How do I pause? If I want to delete 32, right, what happens? It looks for the successor, which is 20. It replaces itself with 20, right? So copy the largest value of lesser tree into the node, yes. Remove the node whose value we copied. Okay. Who inherits the double black? Coloring child of deleted node black. What is this case? Because like the Medium article did not explain this case. Oh man, this is kind of frustrating. 24, 32. No, sorry. 32, 104, 120 or something like that. And then 156. Yes, okay, perfect. Right. And now, let's see, we have the ones that were produced here. Inserting 32, root of the trees red, colored black. Okay. Now, when we insert 24, we should see, you know, a series of observations and stuff. Yeah. The problem is going to be when we delete 104. That's going to be the problem. So remember, the last message was number 20. Everything after 20 is related to this deletion. Deleting 104, found node to delete. Node to delete has two children. Find the largest node in the left subtree. Copy the largest value of the left subtree into the node to delete. Remove the node whose value we copied, coloring child of the deleted node black. Is this just a case that we never saw? Okay, what? What? This is just very irritating because that Medium article did not explain this case. Red, black, tree, deletion. Okay, it's gonna be 7 p.m. I really wanted to finish, but it is getting really frustrating, and I'm pretty sure it's getting really boring for you guys since I'm just going around in circles trying to see what the actual case is because the Medium article did not explain it. So I think this is a natural point to end the stream because like it is it is getting a little, like, a little bit bad. Yeah. So I think I'm gonna end the stream here. I also need to eat dinner. I've been here for 10 hours now. 10 hours. And so it's frustrating that Good didn't get to finish, but like it's just, you know. Swati, you failed us. The dictionary red black tree is a bit tricky than other binary trees. Here I present the delete operation with suitable examples to demonstrate all the cases. Not all the cases are here, Swati. Not all the cases are here. Anyways, it's fine. It's fine. So I don't know. You guys, I think let's end the stream here. I'll try and take a look at this more outside of the stream. It's not as boring. I'm also a little bit tired, and I'm not sure I'm thinking straight. So yeah, I'll see you guys probably tomorrow, maybe if I find a way to solve all of this. I'm really sorry. I really tried, but this red black tree thing is really bad because the guy in the article from which we based the red black tree, I don't know if he just forgot about one case. Like, you saw the table, right? The table just doesn't explain anything. So I don't know. I don't know. Like your hair, by the way. Thank you, Pollywood. Thank you. I don't know. We'll see. I guess I'll see you guys tomorrow. Thank you very much for hanging around. And we've been defeated in a battle, but not in a war, and that's what matters. So you got insane. Yeah, dude. Like, because it's been so long. It's been 10 hours, right? And I wanted to finish it today, but then this random guy from Medium created like a beautiful article because it's super easy to understand, but just didn't describe one case. It seems to me, or maybe I'm reading it wrong. And so now everything is messed up. So I don't know. I hope to see you guys tomorrow. Sorry if the last two streams have been a little bit bad. It's mainly because we've been staying here for so long, and like we've been debugging, and debugging is never fun. So yeah, thank you for hanging around. Mainly because I've got insane. And yeah, I'll see you guys. I'll meet you guys too. I will not meet the right night trees, but I'll still battle with them after the stream. After maybe I eat dinner and disperse my mind, refresh it. But yeah, I'll see you guys. Bye bye. We'll see you tomorrow. Bye bye.